This galaxy is a cosmic car crash frozen in time. The Cartwheel Galaxy, with its stunning ring of blue fire, is not just beautiful, it is profoundly strange. It is the aftermath of a smaller galaxy punching straight through the heart of a larger one, a violent event that created a perfect ring of newborn stars 500,000 light-years across. By the end of this journey, you will understand 50 of its deepest mysteries, from missing black holes to stars born in the wreckage between galaxies. We will see how a single collision can rewrite the rules of an entire galaxy, leaving behind puzzles that challenge our understanding of the universe itself. What do you think happens when two galaxies collide? Its most obvious mystery is also its most beautiful. The Cartwheel Galaxy is not a spiral, not an ellipse, but a perfect cosmic bullseye. This is a ring galaxy, one of the rarest galactic structures we have ever seen. To understand why it looks this way, we need to rewind the cosmic clock by perhaps 500 million years. Back then, this was likely a normal spiral galaxy, minding its own business, its stars orbiting a bright central hub. Then, an intruder arrived. A smaller companion galaxy, perhaps one of those we see nearby today, did not just swing past it. It punched straight through the galactic center like a stone thrown directly into the center of a still pond. The effect was catastrophic and strangely orderly. The gravitational shockwave from that direct hit rippled outward through the galaxy's vast reservoirs of gas and dust. This wave compressed that material, and wherever that dense wave traveled, it lit the fuse for star formation on an epic scale. Think of it as a stellar tsunami. A wall of pressure raced outward, and in its wake, it left a blazing ring of millions of newborn stars. This ring is not a solid object, but a wave of creation, still expanding today at incredible speeds. It is colossal, measuring roughly 150,000 light-years across, meaning light itself would take 150,000 years to travel from one side of this ring of fire to the other. Inside that ring, the older stars of the original galaxy remain, looking ghostly and faint compared to the brilliant blue newborns. Why is this so rare? Because the conditions have to be perfect. The intruder galaxy must hit the center almost dead-on. A glancing blow would just warp the spiral arms into a messy shape. This precise, violent bullseye is what creates such a symmetrical ring, making the cartwheel a textbook example of a phenomenon we almost never get to see so clearly. It is a fleeting cosmic phase, a snapshot of a galaxy literally rearranging itself after a traumatic event. And that perfect ring is just the starting point, the first clue that everything here operates under different rules. But that brilliant ring draws your eye away from something even stranger at the very heart of the galaxy. Look at any classic spiral like our own Milky Way. At its center, you find a crowded, brilliant hub, a dense bulge of ancient yellow and red stars orbiting in a tight, chaotic swarm. This central bulge is the anchor of a normal galaxy. The Cartwheel Galaxy has almost none of it. Where we expect a bright, concentrated core, we instead see a diffuse and faint central region. It glows with a soft, ghostly light, utterly overshadowed by the ring of young stars around it. This is the mystery of the missing central bulge. The colossal collision did not just trigger a ring of new stars, it seems to have dismantled the galaxy's original heart. When that smaller galaxy punched through the center, its gravitational force acted like a cosmic wrecking ball. It likely sent a vast number of the old bulge stars scattering, flinging them out into wider, more chaotic orbits. Imagine shaking a snow globe violently. The glitter inside, once settled at the bottom, becomes a diffuse cloud filling the entire sphere. That is what scientists think happened here. The orderly, dense cluster of ancient stars was puffed out, its structure erased by the sheer violence of the impact. Observations back this up. The core of the cartwheel is not as massive or as active as models predict it should be. There is less light coming from there, suggesting a significant portion of those old stars are simply gone, dispersed into the larger inner region of the galaxy. This raises a profound question. Where did they all go? Were they thrown so far out they now form a faint, invisible halo? Or did the collision's chaos send some of them spiraling out entirely, lost to the emptiness between galaxies? The missing bulge is a silent testament to the unbelievable forces unleashed that day, forces that can erase the defining feature of a galaxy and leave us wondering what else was lost in the chaos. The brilliant ring points a finger back at the culprit. Floating nearby the Cartwheel are two smaller, irregular galaxies, often called G1 and G2 in astronomical images. They look like cosmic bystanders, but one of them is almost certainly the driver that fled the scene. The evidence points to the smaller of the two, the galaxy labeled G2. By studying its current position and, more importantly, its motion, astronomers can trace its path backwards through time. The key clue is velocity. G2 is not just hanging around, it is moving at an incredible speed relative to the Cartwheel, a speed it could only have if it was flung outward by a tremendous gravitational slingshot effect, the exact kind of recoil you would expect from a head-on collision. To solve this cosmic crime, scientists turn to powerful computer simulations. They feed in the current positions, masses, and velocities of all the galaxies involved. Then they run the clock backwards for hundreds of millions of years. These simulations are like forensic recreations of the accident. They test different angles and speeds for the impact, searching for the one scenario that, when played forward, reproduces the perfect ring we see today. The winning model is startlingly precise. It suggests G2 did not just sideswipe the Cartwheel. It shot through its center like a bullet at a staggering velocity of over 200,000 miles per hour. The angle was nearly perpendicular, a direct hit to the galactic core. That perfect, high-speed central impact is what sent the clean, symmetrical shockwave rippling outwards to form the ring. Without that precise violence, we would see a mangled, twisted galaxy, not a cosmic bullseye. So G2 is more than a neighbor, it is a piece of the Cartwheel itself, a fragment that was once part of a larger system, now forever fleeing the scene of the collision it caused. That perfect ring is not a stationary object, it is a moving frontier. What we are witnessing is a propagating wave of star formation, a ripple of creation still expanding across the galaxy hundreds of millions of years after the initial impact. Think of it exactly like a pebble dropped into a still pond. The point of impact is the galactic center where the collision occurred. The gravitational shockwave from that event is the ripple moving outward through the water, which in this case is the galaxy's vast reservoir of diffuse hydrogen gas and cosmic dust. This wave is not made of water, but of pure force. As it travels, it does something extraordinary. It sweeps up the gas in front of it, compressing those giant, cold clouds into incredibly dense knots. And in the universe, when you compress a gas cloud enough, you cross a critical threshold. Gravity takes over, pulling the material inward until the pressure and heat at the core become so intense that nuclear fusion ignites. A star is born. The shockwave did this not once, but billions of times, lighting a fuse that created that entire ring of brilliant blue fire. The youngest, hottest, and most massive stars are right at the leading edge of this wave, blazing with fierce blue light. But look slightly inward from that brilliant edge, and you will see something just as telling. There, the stars are a little older, a few million years into their lives. The most massive of them have already exhausted their fuel and died in spectacular supernova explosions. Their deaths have themselves triggered new rounds of star formation, creating a secondary ripple effect that follows the primary wave. This allows us to read the ring like a cosmic history book. By mapping where the youngest star clusters are versus the slightly older ones, astronomers can literally measure the speed of this stellar tsunami. It has been traveling outward for an unfathomable length of time, and it is still moving, still creating, still writing the next chapter of this galaxy's story on a canvas of cold gas and darkness. The sheer violence of that stellar tsunami has left behind more than just young stars. Scattered throughout the Cartwheel's brilliant ring are objects of almost impossible power, cosmic beacons that defy simple explanation. These are ultraluminous X-ray sources, or ULXs for short. Imagine a single object no larger than a city that outshines our entire sun by 1,000,000 times, but only in high-energy X-ray light. That is the basic profile of a ULX. They are not the supermassive black holes that sit in galactic centers, yet they shine with a similar ferocity from random locations in a galaxy's spiral arms, or in this case, its star-forming ring. The Cartwheel Galaxy is absolutely littered with them, hosting over a dozen of these extreme objects, a concentration that is extraordinarily rare. Their very presence in such numbers is a direct clue that the environment here is unlike anywhere else. So what are they? The leading theories point to two exotic possibilities, both born from the collision's chaos. The first is the intermediate mass black hole. We are familiar with stellar black holes, a few times the sun's mass, and supermassive ones, millions of times heavier. An intermediate mass black hole would sit in the mysterious gap between, weighing perhaps hundreds or thousands of solar masses. Such an object, if it were pulling in gas from a nearby companion star at a furious rate, could glow with the intense X-ray brilliance we see. The second, even more fascinating idea is that these are not black holes at all, but neutron stars on a feeding frenzy. A neutron star is the collapsed, city-sized core of a dead star, so dense a spoonful of its material would weigh as much as a mountain. Under normal circumstances, there is a theoretical limit to how bright a neutron star can get as it consumes material, a limit set by the sheer pressure of its own radiation. But if a neutron star has an incredibly powerful magnetic field, it might be able to funnel incoming gas onto its magnetic poles, bypassing that limit and becoming ultraluminous. The Cartwheel's ring, packed with young, massive stars and the gas clouds from which they formed, provides the perfect buffet for such an object. The abundance of ULXs here suggests the collision did not just make stars. It forged an entire population of stellar corpses that are now feeding at a rate we rarely see, turning the galaxy's beautiful ring into a minefield of some of the most energetic and puzzling objects in the universe. Yet the ring and its strange beacons are not the only scars from the collision. Look more closely at the image of the Cartwheel Galaxy, and you will notice faint, ghostly lines reaching from the dim inner core all the way out to the brilliant outer ring. They look exactly like the spokes on a wagon wheel, giving this galaxy its perfectly fitting name. These are not solid structures, but cosmic filaments, delicate threads woven from dust, gas, and the faint light of ancient stars. They are the enduring fingerprints of the catastrophe, stretched out and preserved across 500,000 light-years. When the smaller galaxy punched through the center, it did not just send a clean ripple outward. It also violently stirred the entire galactic disk, pulling and shearing the material that was there. Think of stirring a cup of coffee with a spoon. The cream doesn't just form a ring, it gets drawn into long, streaming lines that spiral from the center to the edge. On a galactic scale, with unimaginable forces at play, that is what created these spokes. They are fossilized paths, tracing the routes along which material was violently ejected outward from the center, or perhaps drawn back inward by the galaxy's lingering gravity. They are a direct snapshot of the forces in play during those chaotic moments, a map of the chaos frozen in time. Today, these spokes are mostly dark and cold. But their story is being retold by the new generation of stars. The intense star formation happening in the outer ring is so ferocious that its brilliant ultraviolet light is actually illuminating these faint structures, making them visible to our telescopes. It is like turning on a blacklight in a dark room, suddenly revealing the glowing patterns on the walls. Without that ring of newborn stars, these ancient spokes might remain invisible, a hidden skeleton. Their very existence tells us the collision was not a simple, clean event. It was a turbulent, messy process that left its mark in 3 dimensions, connecting the galaxy's wounded heart to its blazing new frontier with threads of cosmic history. The violence of creation is mirrored by the ferocity of destruction. All those brilliant blue stars lighting up the Cartwheel's ring carry a built-in expiration date. They are the giants of the stellar world, dozens of times more massive than our Sun, and they live fast and die young. In a cosmic blink, perhaps only a few million years, they exhaust their nuclear fuel. Their cores collapse and they explode in titanic supernova blasts that outshine entire galaxies for a brief, spectacular moment. The Cartwheel's ring is not just a stellar nursery, it is a supernova factory operating at an industrial scale. This intense, concentrated death leaves behind distinct forensic evidence, supernova remnants. These are the expanding bubbles of multimillion-degree gas and shattered stellar debris, hurled outward by the explosion at thousands of miles per second. In a normal galaxy, such remnants are scattered and relatively rare, but when astronomers point radio and X-ray telescopes at the Cartwheel's ring, they see a stunning overabundance of them. The ring is practically pockmarked with these glowing, expanding bubbles. Each one is a crime scene, the aftermath of a single colossal star's death. But collectively, they become a landscape-shaping force. The combined shock waves from hundreds or thousands of these explosions act like cosmic bulldozers. They sweep up surrounding gas, compress it further, and can even trigger the next generation of star formation, creating a violent feedback loop of birth and death. This relentless cycle paints the ring in a palette invisible to our eyes, a roiling sea of hot gas and energetic particles revealed only by telescopes that see in X-ray and radio light. The sheer number of remnants tells us this galaxy is in the throes of a starburst, a period of frantic, unsustainable creation where stellar life and death are happening on a scale and at a pace we almost never witness. But that violent cycle of stellar death leaves behind a signature of even greater power. Beyond the X-rays and radio waves, the Cartwheel Galaxy seems to whisper in the language of pure energy. Observations hint that the entire galaxy is bathed in a faint, diffuse glow of gamma rays, the most energetic form of light in the universe. This is not a pinpoint beacon like its ultraluminous X-ray sources, but a soft, all-encompassing radiance, as if the galaxy itself is humming with an invisible power. Gamma rays are not emitted by normal stars. They are the signature of the most extreme processes in the cosmos. Their presence here, spread across the whole system, is a profound mystery. So where could this pervasive energy come from? One strong candidate is the very supernova factory we just explored. Each of those thousands of exploding stars acts as a natural particle accelerator, flinging protons and atomic nuclei outward at nearly the speed of light. These become cosmic rays, and when these ultra-fast particles slam into the slower-moving gas and dust that fills the galaxy's ring, the collisions can produce gamma rays. With so many supernovae happening in such a concentrated space, their combined output could indeed create a faint, galaxy-wide glow. It would be the collective roar of all those stellar deaths echoing across 500,000 light-years. But there is another, far more speculative and thrilling possibility whispered among theorists: dark matter. We believe most galaxies, including our own, are embedded within vast, invisible halos of this mysterious substance that interacts only through gravity. The violent collision that created the Cartwheel could have dramatically compressed and concentrated its dark matter halo. If dark matter particles can annihilate each other upon collision, as some theories suggest, then this dense, agitated environment could be the site of countless such annihilations, each one releasing a burst of gamma-ray energy. The diffuse glow could be the first faint signal of dark matter revealing its presence not through its gravity, but through its destruction. While this idea remains highly speculative, it underscores how the cartwheel is not just a beautiful accident, it is a unique laboratory. Its extreme conditions might be amplifying signals from the universe's deepest secrets, forcing us to ask if we are seeing the aftermath of stars or something far more exotic hidden in the galactic wreckage. This faint gamma-ray whisper forces us to look more closely at the raw ingredients of the ring itself, and what we find there is a cosmic contradiction. The Cartwheel's brilliant ring is a stellar nursery of unimaginable scale, a place where massive stars are born, live, and die in supernova explosions that forge heavy elements. Yet, when astronomers analyze the light from some regions of that ring, they discover a puzzling shortage. The metallicity, which in astronomy means the abundance of any element heavier than hydrogen and helium, is surprisingly low. This defies our basic understanding of how galaxies evolve. Think of it like finding a state-of-the-art factory with blazing furnaces and roaring machinery, but the products coming off the line are made only of raw iron ore with none of the sophisticated alloys you would expect. Supernova are the universe's primary forges for elements like carbon, oxygen, silicon, and iron. They blast these newly cooked materials back into space, seeding the surrounding gas cloud so that the next generation of stars and planets can be built from richer, more complex stuff. A region of intense star formation should logically be a region of high metallicity, but in parts of the cartwheel, the chemistry just does not add up. So where did all the heavy elements go? One compelling theory points to the source of the gas itself. When the smaller galaxy punched through, the gravitational shockwave that created the ring swept up vast amounts of material from the outer reaches of the original spiral galaxy. This gas from the galactic suburbs might have been incredibly pristine, largely untouched by previous generations of stars. It was a primordial fuel composed almost entirely of hydrogen and helium from the Big Bang. The ring we see today could be the first generation of stars ever to form from that untouched reservoir, burning pure and blue before they have had a chance to pollute their own environment with the ashes of their deaths. It is a glimpse into the universe's earliest epochs, a pocket of ancient chemistry preserved by a cosmic accident. But there is another, more violent explanation. The massive stars born in the ring are not just factories, they are also tremendous engines of expulsion. Their fierce stellar winds and ultimately their supernova explosions do not just gently recycle material, they can blast it clean out of the galaxy's gravitational grip at incredible speeds. In the cartwheel's unique, loosely bound structure with its missing central bulge and chaotic gravity, this enriched material might be escaping entirely. The heavy elements forged in stellar hearts could be launched on a one-way trip into intergalactic space, lost forever before they can be incorporated into the next round of stars. This would leave the ring perpetually starved of metals, a spectacular but impoverished production line. The low metallicity is not a sign of failure, but a clue to the incredible forces at play. It tells us this galaxy is either showing us a snapshot of the universe's infancy, or it is bleeding its own future building blocks into the void, a beautiful but unsustainable frenzy of creation. Zooming out from the brilliant ring reveals the true scale of the catastrophe. Stretching far into the emptiness, faint arc-like streams of stars and gas drift like ghostly ribbons against the blackness of space. These are tidal tails, the gravitational debris flung out during the collision, and they tell a story of sheer violence that the perfect ring alone cannot convey. When the smaller galaxy tore through the heart of the cartwheel, it did not just rearrange the material it left behind, it also pulled vast amounts of it along for the ride. The immense gravitational forces acted like a cosmic slingshot, yanking billions of stars and enormous clouds of gas completely out of both galaxies. This ejected material, now traveling on its own lonely trajectory, forms these immense curved streams. They are cosmic fingerprints frozen in time. By carefully mapping their shape and curvature, astronomers can trace them back to their point of origin, revealing the precise angle and direction of that ancient impact. A sharp, narrow tail suggests a fast, direct hit, while a broader, more diffuse stream hints at a more drawn-out gravitational tug-of-war. In the Cartwheel's case, the tails are long and relatively thin, confirming the model of a high-speed, piercing collision. But these faint ribbons are more than just forensic evidence. They are a lost ledger of the galaxy's original wealth. By measuring the total amount of light coming from these tidal tails, scientists can estimate how many stars were ripped away. This, in turn, allows them to calculate the original masses of both galaxies before they ever touched. It is a way of weighing a ghost, of reconstructing the victims from the evidence they left scattered at the scene. This lost material also hints at a poignant future. The stars within these tails are now unbound, destined to drift forever in the intergalactic void, forming a faint, diffuse population of orphans. The gas, however, tells a different story. Some of it may eventually fall back into the Cartwheel or its companions over billions of years, providing fresh fuel for future star formation. Other parts may simply dissipate, becoming part of the tenuous web of matter that filaments the cosmos. The tidal tails are a reminder that a galactic collision is not a closed event. It is an explosion whose echoes travel for billions of years, scattering the very building blocks of worlds into the endless dark. Those ghostly tidal tails are not the only structures hiding in the deep dark. Some astronomers studying the Cartwheel have reported a faint, tantalizing whisper of something even more peculiar. There are hints, subtle and still debated, of a secondary ring. This would not be another ring in the same plane, but a loop of gas and ancient stars orbiting at a right angle to the brilliant blue ring, like a hula hoop spinning around a dinner plate. If confirmed, this would transform the Cartwheel from a rare ring galaxy into an almost mythical cosmic object, a polar ring galaxy. Such a structure would wrap around the galaxy's poles, tracing a path perpendicular to its main disk. How could such a bizarre configuration even happen? The leading theory points to a second act of galactic cannibalism, separate from the collision that made the main ring. Long ago, a small dwarf galaxy, rich in gas but poor in stars, could have been captured by the Cartwheel's gravity. Instead of merging directly, it might have been torn apart and its remains stretched into a vast, looping orbit that circles over the galactic poles. Over billions of years, the gas from that devoured dwarf would settle into this perpendicular ring, and new stars would slowly ignite within it, creating a faint, orthogonal halo. For the Cartwheel, this would mean its history is even more violent and complex than we thought, a story of not one but two separate galactic encounters. The evidence, however, is maddeningly elusive. The suspected polar ring is incredibly faint, buried in the glow of the main galaxy and the blackness of space. Different telescopes and different analysis techniques have yielded conflicting results. Some see a clear, coherent structure, while others see only random clumps of gas that could be mistaken for a ring. The search for conclusive proof is a meticulous forensic process, requiring astronomers to carefully subtract the overwhelming light of the main disk to see if any coherent pattern remains in the leftover glow. Finding a true polar ring would be a monumental discovery. It would act as a cosmic gyroscope, allowing scientists to map the invisible gravitational field of the entire galaxy in 3 dimensions, revealing the distribution of its dark matter halo in a way few other structures can. The debate continues, a quiet scientific mystery playing out in the faintest whispers of light from 500 million light-years away. Is the Cartwheel hiding a secret, perpendicular skeleton, or are we seeing cosmic shadows on the wall? The answer would redefine just how strange this galaxy truly is. The faint whispers of a possible polar ring lead our eyes back to the main event, where the ring's blue fire reveals its own strange knots of light. Scattered along that brilliant loop are several intense, compact patches that outshine everything around them, Astronomers call them blue blobs, and they are far more than just dense star clusters. Each one is a stellar metropolis, a city of millions of stars packed into a region just a few thousand light years across, glowing with an almost impossibly fierce blue light. Their extreme brightness and color tell us they are not just old neighborhoods of the original galaxy, they are something entirely new, forged in the violence of the ring. The leading theory is as astonishing as it is beautiful. These blobs may be tidal dwarf galaxies in the very act of being born. When the collision ripped through the cartwheel, it did not just stretch gas into faint tidal tails, it also flung out massive, dense clouds of gas and dust. Some of these clouds were so enormous and self-contained that their own gravity began to pull them together, separate from the main galaxy. Within these isolated cocoons of material, star formation ignited on a galactic scale. These are not galaxies that existed before the crash, they are new worlds built from the wreckage. A tidal dwarf galaxy is a cosmic phoenix, a new island universe born from the ashes of a violent encounter. If the blue blobs are indeed these infant galaxies, then the cartwheel is not just recovering from a collision, it is actively giving birth. It is creating its own future satellite galaxies right before our eyes, sculpting them from the very ring that marks its own wound. But the story has a twist. The intense gravitational pull of the massive cartwheel looms over these fledgling systems. Some of these blobs may not survive to become independent galaxies. Instead, they could be in the process of being cannibalized, their stars and gas slowly being pulled back into the main ring by tidal forces. We might be witnessing both creation and destruction in the same brilliant patches, a simultaneous birth and digestion happening on a galactic scale. This turns the ring into a dynamic ecosystem of gravity, where new worlds coalesce from chaos only to potentially be consumed by the very parent that spawned them. Are the blue blobs the cartwheel's children, or are they merely its next meal? Their brilliant blue light holds the answer, a signature of youth that will fade as their most massive stars die, revealing whether these knots of light will mature into companions or simply dissolve back into the fiery ring from which they came. That brilliant blue light hides a lopsided heartbeat. When astronomers tune their radio telescopes away from the visible spectrum and listen to the cartwheel's deeper song, they find a profound asymmetry. The galaxy's radio emission, a telltale sign of high-energy activity, is not a perfect halo. One side of the colossal ring glows far more brightly in radio waves than the other, as if the galaxy has a stronger, more active pulse on one side of its body. This is not a flaw in the image, it is a fundamental clue written in the language of charged particles and magnetic fields. Radio waves in a galaxy like this are primarily generated by two violent processes, the expanding shells of supernova remnants and the frenetic spiraling of electrons around magnetic field lines. A symmetrical ring should, in theory, produce a symmetrical radio glow. The fact that it does not mean something is fundamentally unbalanced in the cartwheel's engine room. One compelling explanation points directly to the supernova factory we explored earlier. The wave of star formation might not be a perfectly even ripple. It could be moving through a patchy, uneven sea of gas. If one segment of the ring encountered a much denser cloud of primordial fuel, it would have triggered an even more intense burst of massive star birth. More massive stars mean more supernova, and more supernova mean a greater concentration of those expanding, radio-bright remnants. That one overachieving section of the ring would then shine like a beacon to radio telescopes, a hotspot of stellar death and renewal. But there is another, more external possibility. The cartwheel is not floating in a perfect vacuum. It is moving through the tenuous intergalactic medium, the thin soup of gas that filaments the cosmos. If the galaxy is plowing through this medium at an angle, one side of the ring would be ramming into it head-on. This would create a bow shock, compressing the galaxy's magnetic fields and accelerating particles on that leading edge, causing it to glow more brightly in radio waves. Think of it like running through a mist. The front of your body gets wetter than the back. The radio bright side could simply be the side facing the direction of travel, wearing a cloak of interstellar friction. The most intriguing possibility, however, reaches back to the collision itself. What if the impact was not perfectly centered after all? Even a slight deviation from a dead center hit would have sent a stronger, more focused shockwave in one direction. That initial asymmetry, frozen into the expanding ring hundreds of millions of years ago, could still be echoing today. The brighter radio lobe might mark the direction of the original punch's strongest force, a permanent scar of directional violence. This lopsided signal forces us to question the very perfection of the cartwheel's form, suggesting its beautiful symmetry is only skin deep, and beneath that brilliant ring lies a history of messy, unbalanced violence that still dictates where the galaxy's energy flows. That lopsided radio heartbeat points to a deeper silence at the very center of the storm. Galactic collisions of this ferocity are not just about making stars, they are also about feeding monsters. At the heart of nearly every large galaxy, including our own, lurks a supermassive black hole, a gravitational pit millions or even billions of times heavier than our Sun. When such a black hole actively pulls in vast amounts of gas, that material doesn't just vanish. It swirls into a blazing, ultra-hot disk of doomed matter, becoming the most luminous object in the universe, a quasar. The logic seems inescapable. A smaller galaxy punches straight through the cartwheel's core, an event of unimaginable violence that should have sent tsunamis of gas swirling directly toward that central black hole. The collision should have been the ultimate dinner bell, triggering a quasar so bright it would outshine the entire galaxy. Yet when we look, we find a puzzling quiet. The cartwheel's core is dim, a faint smudge compared to the brilliant ring. So where is the quasar? This is the mystery of the missing monster, and it forces astronomers to question their models of how these cosmic beasts awaken. One possibility is simple: the black hole is just dormant. Perhaps the collision, while violent on a galactic scale, was strangely tidy on the small scale of the core. The gravitational shockwave might have pushed gas outward into the ring more efficiently than it funneled gas inward toward the black hole. Think of a powerful explosion in a room. It might blow out the windows more easily than it pushes debris into a small hole in the floor. The black hole could be starving, sitting in a cleared-out cavity, waiting for gas to eventually fall back in over billions of years. Another, more dynamic idea involves a time delay. The process of feeding a supermassive black hole is not instant. Gas has to lose an enormous amount of angular momentum, essentially its spin, to spiral all the way down into the gravitational well. This can take tens or even hundreds of millions of years. The brilliant ring we see is the immediate, flashy result of the collision, but the feast for the central black hole might be a much slower, more drawn-out affair. We could be living in the quiet pause between the dinner bell ringing and the monster finally beginning to eat. A quasar might ignite in the cartwheel's core long after humanity is gone, a delayed cosmic firework from an ancient crash. There is also a more violent possibility. The initial feeding frenzy might have already happened and ended. A brief, fierce burst of accretion could have occurred immediately after the impact, lighting up the core as a quasar for a few million years. But that very activity, the intense radiation and powerful jets from the black hole, could have blown away the remaining fuel supply, shutting off its own meal and leaving the core in the quiet state we see today. The cartwheel's silent heart, therefore, isn't proof of a failed trigger. It could be the aftermath of a brief, spectacular feast that we simply missed by a cosmic eyelash. This quiet center challenges the neat story we want to tell, reminding us that even the most predictable cosmic violence has unpredictable consequences, and that the most terrifying monsters sometimes sleep through the apocalypse. The silence of its central black hole forces us to look for the galaxy's true mass in the invisible realm. While the brilliant ring tells one story, the cartwheel's hidden gravitational skeleton may tell another, and that skeleton is built from dark matter. Galactic collisions are the ultimate experiments for this mysterious substance because dark matter, by its very definition, does not behave like normal matter. It does not crash, compress, or glow. It feels only gravity and should simply pass through itself like a ghost. This means that during a head-on collision like the one that created the cartwheel, the dark matter halos of the two galaxies should do something extraordinary. They should slip right through each other, largely unaffected, while the normal gas and dust smash together violently to form the visible ring. If this theory is correct, then today, hundreds of millions of years later, the cartwheel's dark matter halo should be in a completely different place than its dazzling ring of stars. It should be offset, distorted, or perhaps even lagging behind the visible galaxy entirely. So how do we weigh a ghost? Astronomers have two powerful tools for this cosmic detective work. The first is gravitational lensing. If the cartwheel's gravity is strong enough, it will bend the light from more distant galaxies behind it, acting like a flawed lens. By meticulously mapping these subtle distortions, scientists can create a mass map of the entire system. Where the mass is concentrated, the lensing effect is stronger. If the peak of that mass map does not align perfectly with the bright ring of stars, it would be direct evidence that the majority of the mass, the dark matter, is somewhere else. The second tool studies motion within the galaxy itself. By measuring the rotation speeds of stars and gas clouds at different distances from the center, astronomers can calculate how much mass must be present to hold them in orbit. If the visible mass from stars and gas is far too little to explain those high speeds, the missing mass must be dark matter. By creating a detailed velocity map of the cartwheel, scientists could pinpoint where that extra gravitational grip is strongest, revealing the shape and distribution of its invisible halo. A clean separation between the visible ring and the peak of the dark matter would be a monumental discovery. It would be like seeing a car crash where the passengers were thrown clear but their shadows remained frozen in the seats. A direct visual proof that dark matter is real and behaves exactly as predicted. The cartwheel, with its clean, violent history, offers a uniquely clear laboratory for this test. Its perfect ring is the control, the known outcome of normal matter. Any gravitational anomaly is the signature of the unknown. Studying this galaxy isn't just about understanding a collision. It is about using that collision to illuminate the universe's deepest secret, hunting for the ghostly outline of the stuff that holds everything together. The hunt for dark matter leads us to a different kind of hidden signature, one written not in gravity but in heat. The Cartwheel Galaxy possesses a startling infrared luminosity excess. In plain terms, it glows with a fierce, deep warmth that far outshines its brilliant blue visible light. If our eyes could see in the infrared spectrum, this galaxy would appear as a blazing crimson bullseye, radiating more energy in this hidden light than in all the starlight our telescopes can capture. This is not a subtle difference, it is an overwhelming thermal roar. The source of this immense infrared glow is not the stars themselves, but what lies in the spaces between them, cosmic dust. The collision that created the ring did not just compress gas to form stars, it also churned up and manufactured staggering amounts of fine, sooty particles, the ashes of stellar furnaces and the shattered remains of complex molecules. This dust is not like household dust. It is a mist of tiny silicate and carbon grains, smaller than a wavelength of visible light, and it is everywhere, especially concentrated in that star-forming ring. When the intense ultraviolet light from all those newborn massive stars slams into these microscopic grains, they do not reflect it, they absorb it. They heat up from a few tens of degrees above absolute zero to a cozy, glowing warmth. And then they re-radiate that absorbed energy, but they do so at much longer wavelengths in the infrared part of the spectrum. It is the same principle as asphalt heating up in the sun and radiating warmth you can feel on your skin long after sunset. The Cartwheel is doing this on a galactic scale, its entire ring acting as a colossal radiator, soaking up the fury of its own starbirth and releasing it as a pervasive infrared glow. This dust does more than just glow, it also hides. It acts as a thick cosmic fog, obscuring our view of the very star-forming regions that are heating it. To the Hubble Space Telescope, which sees primarily invisible light, the ring appears as brilliant blue clusters separated by dark lanes. But those dark lanes are not empty, they are choked with this obscuring dust. This is where infrared telescopes become our eyes into the hidden heart of the chaos. The Spitzer Space Telescope was a pioneer in this, its infrared vision piercing the dusty veils to reveal that star formation was not just happening in the visible clusters, but was rampant throughout those dark lanes as well. It showed us that the Cartwheel's stellar baby boom was even more intense and widespread than we thought. Now, the James Webb Space Telescope has taken this revelation to an entirely new level. Webb's exquisite infrared sensitivity and resolution allow it to do more than just see through the dust. It allows us to map the thermal structure of the entire galaxy in breathtaking detail. We can see the temperature gradients across the ring, pinpointing the hottest dust right next to the youngest star clusters and tracing how that heat dissipates into the colder, more diffuse regions. It can even identify the chemical fingerprints of complex molecules frozen onto those dust grains. This infrared excess is therefore not just a curious side effect, it is a vital diagnostic tool. By measuring the total infrared luminosity, astronomers can calculate the total rate of star formation hidden by dust, a number that would be a severe underestimate if we relied on optical light alone. It reveals the true, frenetic pace of creation in this galactic wreck, showing that for every brilliant blue star we see, there are likely dozens more being born behind curtains of cosmic soot, their first light transformed into a warm, infrared whisper that tells the true scale of the cataclysm. That pervasive infrared glow from cosmic dust is just one layer of the Cartwheel's hidden anatomy. To understand the true engine of this galaxy, we must map its most fundamental fuel, hydrogen gas. This is the raw, cold material from which every star in that brilliant ring was forged. Using powerful radio telescopes tuned to the specific frequency that neutral hydrogen emits, astronomers have created a detailed map of this primordial fuel across the entire galaxy. And what they found was not a perfect match for the beautiful optical image. The hydrogen does not align neatly with the blazing blue ring of young stars. Instead, it forms a broader, more diffuse halo that seems to either lead ahead of the stellar wave or lag curiously behind it, depending on which segment of the ring you examine. This mismatch is a profound clue, a sign that the physics of this propagating ring is far more complex than a simple ripple in a pond. Hydrogen gas and newborn stars are telling two different stories about the same event. One possible explanation involves sheer momentum. When the gravitational shock wave initially compressed the gas to trigger star formation, it did not use up all the fuel. The wave itself, that wall of pressure, might have continued to plow through the galactic disk, pushing a vast reservoir of hydrogen gas ahead of it like a cosmic snowplow. In this scenario, the densest hydrogen would be found just beyond the leading edge of the youngest stars, a stockpile of fuel waiting for the next round of compression and ignition. Alternatively, in other areas, the gas might appear to lag. This could happen if the star formation process is incredibly efficient and rapid, burning through the local hydrogen so quickly that the visible ring of stars marks where the fuel has already been consumed, leaving a depleted zone behind it. But there is a more violent possibility at play: gas stripping. The Cartwheel is moving at high speed through the tenuous intergalactic medium. This could act like a fierce wind, blowing the lighter, more diffuse hydrogen gas away from the denser star clusters. The gas, being more easily displaced, gets pushed out of alignment, creating a smeared and offset distribution compared to the brighter, more anchored stars. Furthermore, the intense radiation from all those massive stars heats the surrounding hydrogen, preventing it from cooling and collapsing to form the next generation. This creates a complex feedback loop where star formation in one area can actually shut it down in adjacent regions, leading to a patchy and misaligned map of fuel and fire. This anomalous hydrogen map forces us to see the cartwheel not as a static painting, but as a dynamic and messy engine. The perfect ring is an illusion of youth and light. The hydrogen tells the older, slower, and more chaotic story of the fuel supply chain, revealing a system where the raw materials are being moved, heated, and consumed in a turbulent cycle that we are only beginning to decode. The brilliant blue fire of the ring casts a long shadow over the galaxy's own history. Scattered among those dazzling young clusters, astronomers expected to find the quiet, ruddy glow of ancient stars, the original inhabitants from before the catastrophic collision. These older stars, cooler and redder than their massive blue neighbors, should be everywhere, a background population telling the story of the galaxy's first several billion years. Yet when they search, these old stars seem to be missing in action. Their apparent scarcity is a quiet but profound puzzle. Where did the galaxy's original stellar population go? The first and simplest explanation is cosmic camouflage. The cartwheel's ring is choked with the very dust that creates its fierce infrared glow. That same dust could be acting as a thick veil, obscuring the faint red light of older stars that lie behind or within it. From our distant vantage point, their gentle glow might be completely swallowed by the dusty fog, making them invisible to our optical telescopes. It would be like trying to see a candle's flame through a dense cloud of smoke while a searchlight is shining directly into your eyes. The searchlight is the blue starlight and the smoke is the dust. If this is the case, then the old stars are not truly missing. They are just hidden, waiting for infrared eyes like the James Webb Space Telescope to peer through the obscuration and finally reveal their ancient light. But there is a second, more violent possibility. The collision that created the ring was not a gentle event. When the smaller galaxy punched through the core, the gravitational forces were so extreme they could have done more than just puff out the central bulge. They might have violently scattered a significant fraction of the original disk stars entirely, flinging them out into the galaxy's extended halo or even ejecting them into intergalactic space altogether. In this scenario, the old stars are not hidden, they are gone. The ring we see today would be built largely from gas that was already in the outer disk, gas that had not yet formed many stars, making the current stellar population overwhelmingly young. This would mean the cartwheel is not just wearing a new ring, it is wearing a new face with much of its original identity stripped away and lost to the void. A third, more subtle idea suggests the old stars are present but utterly outshone. The brilliance of those massive blue stars is so intense, their light so overwhelming, that it could simply drown out the faint, redder glow of their older neighbors in the same region. Our telescopes, when looking at the ring, see the combined light of all the stars in a given pixel. If that pixel contains one incredibly bright blue star and 100 faint red ones, the blue light dominates completely, washing out the red signal. Distinguishing the old population would require meticulous statistical analysis, carefully subtracting the known light of the young stars to see what faint residue remains. This is a painstaking astronomical detective game. The answer matters deeply because it holds the key to the galaxy's pre-collision state. If the old stars are merely hidden, then the cartwheel was a normal, mature spiral before the crash. If they were violently scattered, it suggests the collision was even more disruptive than we imagined, erasing the galaxy's past on a fundamental level. Finding these missing ancient stars is like finding the foundation of a house after a hurricane. It tells us what was there to begin with and just how much of the original structure survived the storm. The search for those ultraluminous X-ray sources leads us to a more specific and more violent possibility. Among the dozens of brilliant beacons in the Cartwheel's ring, some may not just be feeding black holes or neutron stars, they might be miniature versions of the universe's most powerful engines. These are microquasar candidates. To understand what that means, picture a quasar, the dazzling core of a distant galaxy, powered by a supermassive black hole swallowing stars and gas. Now shrink that entire system down to stellar scales. A microquasar is a stellar mass black hole or a neutron star, but one that is not just quietly feeding. It is launching twin beams of matter and energy that race away from it at nearly the speed of light, relativistic jets that can stretch for light years across space. These jets are the signature of a system in an extreme state of accretion, where material is falling in so rapidly and chaotically that a fraction of it gets channeled and blasted away along the object's magnetic poles. Finding such an object in the Cartwheel would be a game changer. It would directly explain the mind-bending X-ray output of some of those ULXs, as the intense friction and magnetic fields near the jet base generate tremendous heat and radiation. But more than that, it would offer a rare chance to study jet physics in a laboratory unlike any other. The Cartwheel's ring is not a normal galactic environment. It is packed with young, massive stars, dense gas clouds, and the turbulent remnants of supernova. A microquasar's jets here would not be firing out into empty space. They would be plowing directly into this dense, messy interstellar medium. We could watch in real time on a cosmic scale how those relativistic jets interact with the surrounding material. Do they carve out vast bubbles in the gas? Do they trigger secondary waves of star formation by compressing nearby clouds? Or do they get stifled and choked by the sheer density of their surroundings, their energy dissipated as heat and radio waves? This is why radio observations are the key to the hunt. While X-rays tell us about the intense activity right at the mouth of the monster, radio telescopes can trace the extended structure of these jets. Astronomers are meticulously scanning the Cartwheel's ring, searching for the telltale paired lobes of radio emission that would signal a microquasar at work. Finding even one would transform our view of the ring. It would mean that within this colossal stellar nursery, some of the most exotic and energetic objects in the cosmos are not just shining, they are actively reshaping their immediate neighborhood with beams of power that rival those of galaxies 1 billion times their size. The chaos of creation extends into an invisible dimension woven through the very fabric of the Cartwheel's being. This galaxy is not just a collection of stars and gas, it is a maelstrom of magnetic force. Galactic collisions do more than rearrange matter. They twist, stretch, and amplify magnetic fields into a state of profound turbulence. The Cartwheel's magnetosphere is likely a chaotic mess, a cosmic snarl of magnetic lines of force that have been violently stirred by the impact and the subsequent frenzy of stellar birth and death. We cannot see these fields directly, but we can trace their ghostly outline through a phenomenon called polarized radio emission. As fast-moving electrons spiral along magnetic field lines, they emit radio waves that have a specific orientation or polarization. By carefully mapping this polarized light across the galaxy, astronomers can infer the structure of the invisible magnetic web. In a calm spiral galaxy, these fields often follow the orderly pattern of the spiral arms. In the Cartwheel, the map would tell a story of pure pandemonium. The fields are probably shredded, looped, and compressed into knots, mirroring the violent churn of the gas from which they emerge. This turbulent magnetosphere is far from a passive bystander. It is an active and powerful engine. Those tangled magnetic fields act as a natural, galaxy-sized particle accelerator. Charged particles like protons and electrons can get caught in these whirling magnetic vortices and be whipped to velocities approaching the speed of light, becoming the cosmic rays that permeate the galaxy. This process directly contributes to the Cartwheel's unusual multi-wavelength emissions. from the radio glow of those spiraling electrons to the gamma-ray whispers that might come from their collisions. Furthermore, this magnetic chaos influences the very process of star formation itself. Magnetic fields provide a form of cosmic pressure that can support gas clouds against their own gravity, slowing their collapse. In the Cartwheel's ring, where the gravitational shockwave was so overwhelming, it may have compressed the magnetic fields along with the gas, temporarily overwhelming this magnetic support and allowing for that explosive burst of star formation. But now, in the aftermath, the re-amplified and tangled fields could be regulating the next phase, either stifling new star birth or channeling flows of gas in unpredictable ways. The Cartwheel's beautiful ring, therefore, is held together by more than gravity. It is laced with an invisible, frenetic skeleton of magnetic force, a hidden architecture of power that turns the entire galaxy into a roaring particle accelerator and a crucible of magnetic mayhem. But the faint whispers of magnetic mayhem are not the only ghostly echo in the Cartwheel's portrait. Some of the deepest, most sensitive images ever taken of this galaxy hint at something even more unsettling. Beyond the brilliant blue outer ring, there are faint suggestions of a second, far larger ring structure, a ghostly ripple in the cosmic pond. This is not the debated polar ring, but a second concentric circle, a faint, gargantuan halo that would dwarf the already colossal ring we know. The evidence for this second ring is maddeningly tenuous, appearing only in the most meticulous observations that push our telescopes to their absolute limits. It is not a structure you can point to with certainty, more a subtle statistical excess of faint light at a specific, enormous distance from the galaxy's core. If it is real, it would force us to completely rewrite the Cartwheel's violent biography. One possibility is that we are seeing the fossil of a much older, more ancient collision. Imagine a smaller galaxy striking the Cartwheel's predecessor not once, but twice in two separate cosmic epochs separated by perhaps 1 billion years. The first impact would have created that faint, now barely visible outer ring, which then faded as its stars aged and died. Then, much later, the second, more recent collision with galaxy G2 punched through again, creating the brilliant blue ring we see today inside the ghost of the first. This would make the Cartwheel a palimpsest of violence, a galactic manuscript where one cataclysm is written over the erased text of an older one. Another, even more mind-bending explanation involves not a second impact but a complex resonance effect. The gravitational shockwave from the single known collision could have triggered not one, but multiple ripples in the galactic disk, like a drumhead vibrating at several harmonics at once. The main ring would be the fundamental frequency, the strongest and brightest wave. This faint outer ring could be a secondary harmonic, a weaker but wider ripple that traveled outward at a different speed, compressing gas less efficiently and creating only a sparse sprinkling of stars. If true, it would mean a single event can write its signature across a galaxy in multiple, overlapping waves, a cosmic echo that lingers for eons. Proving or disproving this second ring is a monumental technical challenge. Astronomers must perform a kind of cosmic archaeology, digitally peeling away the overwhelming light of the main galaxy, its bright ring, and even the glow of the night sky itself, searching for any coherent pattern in the leftover whisper of photons. The discovery of a true second ring would transform the Cartwheel from a stunning accident into a layered chronicle of repeated trauma, a galaxy that seems to attract catastrophe, each impact leaving its own faint scar in the stellar record. Those ghostly whispers of a second ring are not the only spectral mysteries hiding in the Cartwheel's light. When astronomers dissect its fierce infrared glow with the precision of a prism, they find a set of chemical fingerprints that do not match any simple substance. These are the unidentified infrared bands, a series of specific wavelengths where the galaxy emits a little extra energy, like bright lines on a barcode that we cannot yet fully read. For decades, these bands have been a puzzle throughout our own Milky Way, but in the Cartwheel, they shine with unusual strength and tell a unique story. The leading suspect for creating these spectral signatures is a family of complex organic molecules known as polycyclic aromatic hydrocarbons. That is a mouthful, so we call them PAHs. Picture them not as a liquid or a gas, but as microscopic flakes like the soot from a candle flame or the char on a piece of grilled food, but floating in the vast emptiness of space. Their structure is surprisingly elegant, tiny flat sheets of carbon atoms arranged in hexagonal rings, often with hydrogen atoms fringing the edges. They are essentially the building blocks of soot and potentially the raw ingredients for even more complex chemistry. The fact that they exist in such abundance within the Cartwheel's chaotic ring is astonishing. It means that amid the violence of colliding galaxies and the fury of newborn stars, the fundamental pieces for organic chemistry are not just surviving, they are thriving. The intense ultraviolet light from massive stars, which you would think would shred delicate molecules, actually plays a dual role. It can destroy them, but it also excites them. When a PAH molecule absorbs a photon of ultraviolet light, it begins to vibrate like a tuning fork struck hard, and then it re-emits that energy at very specific infrared wavelengths, creating those characteristic unidentified bands we detect. Their distribution across the ring is a map of both creation and destruction. They are most abundant not in the very hottest zones right next to the youngest stars, where the radiation field would tear them apart, but in the slightly more sheltered neighborhoods just adjacent. It is as if they flourish in the suburbs of stellar chaos, in the dense clouds where starlight is strong enough to make them sing, but not so fierce as to obliterate them. By studying the strength and pattern of these bands, astronomers can take the temperature of the interstellar environment in a way that starlight alone cannot reveal. They act as microscopic thermometers and chemical probes, telling us how harsh the radiation field is, how dense the gas clouds are, and how efficiently complex chemistry can proceed in the aftermath of a galactic wreck. The Cartwheel, therefore, is more than a stellar factory. It is a sprawling chemical plant. Within its fiery ring, amid the birth of stars and the death of giants, the universe is quietly, persistently assembling the complex organic seeds that, in other places and other times, could be the first step toward the chemistry of life. This chemical complexity paints the ring in a subtle, shifting palette of light. The Cartwheel's brilliant blue ring is not a uniform band of color. It is a canvas of gradients, a slow fade from one hue to another that holds the timeline of the catastrophe. From its sharp, bright inner edge to its slightly softer outer boundary, the ring shifts in shade, a chromatic story written across 500,000 light-years. Blue, in the language of starlight, is the signature of youth and ferocity. It tells us a star is extremely hot, massive, and burning its nuclear fuel at a reckless pace. The most intense, piercing blue light comes from stars that are only a few million years old, stellar infants on a cosmic scale. As you look outward across the width of the ring, that blue can soften, taking on a slightly whiter or even a faintly reddish tint. This is not a flaw in the image, it is a critical clue. A slightly redder hue can mean one of two things. First, it could indicate that the stars in that region are just a few million years older. As massive stars age, even over a short span of 10 million years, they cool slightly and their light shifts toward the red end of the spectrum. A gradient from piercing blue on the inner edge to a softer blue-white further out would be a direct map of the wave's passage, with the oldest stars in that wave marking where it began its expansion. Second, that reddening could be the fingerprint of dust. The same microscopic grains that create the fierce infrared glow also act like a cosmic filter, scattering and absorbing blue light more effectively than red light. A region that is particularly rich in dust will make the stars behind it appear redder, as if seen through a haze of interstellar smoke. By carefully separating these two effects, astronomers can perform a remarkable feat of cosmic cartography. They can chart the precise history of the star-forming wave. The leading, outermost edge of the ring should be the purest, most intense blue, marking the very frontier where the shockwave is currently compressing gas and lighting new stellar fires. Just behind that edge, the blue might be slightly less intense, as the very first stars born in that region have had a few million years to age, and the dust from their formation begins to accumulate. Further in still, the light might be more filtered, as successive generations of supernova have polluted that zone with complex dust, reddening the glow of the stars that remain. This color gradient is therefore a timeline frozen in space. By reading it, we don't just see a ring, we see a history book open to a specific chapter. We can trace the wave's speed not by guessing, but by measuring the physical distance between the youngest blue stars and the slightly older ones. We can identify regions where star formation happened in a single, clean burst, and others where it has been messy and prolonged, leaving behind a patchwork of different aged clusters. This subtle shift in color, almost invisible to the casual glance, reveals that the Cartwheel's perfect ring is not a simultaneous event, but a rolling revolution of creation, its story told in the fading light of its own brilliant children. That subtle color gradient is a map of history, but the Cartwheel's gravity is writing a different map on the fabric of space itself. Its immense mass, concentrated in stars, gas, and that vast hidden halo of dark matter warps the space around it. This means it should act as a flawed and fuzzy cosmic lens, a phenomenon known as weak gravitational lensing. The gravity of the entire Cartwheel system subtly bends the paths of light rays from much more distant galaxies that lie far behind it in our line of sight. It does not create multiple images or dramatic rings like a perfect alignment would, but it does gently stretch and distort the shapes of those background galaxies, making them appear slightly more elongated in a direction that circles the Cartwheel's mass. This effect is a direct probe of total gravity and therefore total mass. It is the universe's own scale, weighing everything, visible and invisible, in one measurement. Detecting this subtle signal, however, is a monumental challenge of cosmic needlework. The primary obstacle is the Cartwheel's own dazzling, complex light. That brilliant ring and its ghostly spokes are a foreground fireworks display that completely overwhelms the faint, distorted smudges of the background galaxies. Trying to measure the weak lensing effect here is like trying to detect the ripples from a pebble dropped in a pond while a speedboat is churning up waves in the middle of it. Astronomers must perform meticulous digital surgery, using sophisticated software models to carefully subtract the precise light profile of the Cartwheel itself from their deepest images. Only after peeling away this overwhelming foreground glow can they hope to see the population of faint, distant galaxies behind it with enough clarity to measure their tiny, systematic distortions. The potential prize for this painstaking work, however, is worth the effort. If successful, a weak lensing map would provide an independent and powerful check on the galaxy's mass distribution. All other methods, like measuring the rotation speeds of gas within the ring, rely on assumptions about how that material is moving under the influence of gravity. Gravitational lensing makes no such assumptions. It simply measures the total gravitational pull from all sources, in all places, by seeing how space itself is curved. A detailed lensing map could show us exactly where the Cartwheel's mass is concentrated. The critical question is whether the peak of that mass aligns with the bright ring of young stars or if it is offset. If the greatest gravitational tug comes from a location that does not match the visible light, it would be stunning, direct evidence that the dark matter halo was indeed displaced by the collision, lagging behind or spread differently than the visible wreckage. It would be like finding that the heaviest part of a spinning figure skater is not their body, but an invisible weight floating off to the side. This independent measurement could settle debates about the galaxy's true mass, the behavior of dark matter in collisions, and even help calibrate our other methods for studying this chaotic and beautiful system. The faint, stretched shapes of galaxies billions of light years behind the cartwheel hold the key to weighing the ghost that shapes it. The brilliant chaos we see forces us to look for the architect of the wreckage. So what happened to the galaxy that punched through the heart of the cartwheel? The evidence points a clear but incomplete finger at the smaller of its two visible companions, the galaxy astronomers labeled G2. This is not just a neighbor, it is a suspect fleeing the scene. Its trajectory tells the story. G2 is moving at an astonishing speed relative to the cartwheel, a velocity it could only have gained from the gravitational slingshot of a direct high-speed impact. Think of it like a bullet ricocheting from a steel plate, the force of the collision propelling it away at tremendous speed. This motion is our first major clue. The second clue is its condition. G2 appears ragged and irregular, stripped of much of its gas and dust. This is exactly what we would expect from a galaxy that plowed through the dense central disk of a larger spiral. The cartwheel's gravitational pull, combined with the sheer friction of moving through that thick interstellar medium, would have acted like a cosmic cheese grater, scraping away the smaller galaxy's gaseous envelope and leaving it gas-poor and misshapen. This explains why, despite its violent history, G2 is not forming many new stars today. It has lost the primary fuel for stellar birth. But what about the other visible companion, the larger galaxy labeled G1? Its role is more ambiguous. It may have been a bystander, a satellite galaxy that was simply along for the ride, its own structure distorted by the gravitational wake of the main collision. Or, in a more complex scenario, G1 could have interacted with G2 before or after the central impact, a three-bodied dance of gravity that further complicated the chaos. The most likely story, supported by sophisticated computer simulations, is that G2 was the bullet. It shot through the cartwheel's core on a nearly perpendicular path, creating the clean shockwave that formed the ring, and was then flung outward, wounded and gas-stripped to where we see it now. But this is not the end of the story. Gravity is a patient force. While G2 is currently fleeing, its trajectory is not a straight line out of the system. It is still bound by the cartwheel's immense gravitational pull. Over the next few billion years, that pull will act as a tether, slowly curving its path. G2 will reach a maximum distance, a sort of cosmic apogee, and then begin to fall back in. This sets the stage for a second, final act. Billions of years from now, G2 will likely merge completely with the cartwheel's core. This second merger will be slower and messier than the initial piercing collision. Without a large gas reserve, it will not trigger another spectacular ring. Instead, it will be a stellar merger, a slow gravitational tango that will puff up the cartwheel's central regions, adding its stars to the galaxy's halo and further stirring up any remaining material. As for G1, its fate is tied to the same gravitational web. It too will eventually be drawn in, leading to a long, drawn-out process where all three galaxies coalesce into a single, larger elliptical galaxy, a smooth and featureless island of old stars that bears no visible trace of the beautiful ring or the violent history that created it. The cartwheel's stunning form is therefore a transient masterpiece, a brilliant but fleeting chapter in a multi-billion-year story of attraction, collision, and ultimate unification. The intruder galaxy is both the destroyer and the future building block, destined to return and complete the destruction of the beauty it created. The violence of those stellar deaths carves the ring into a cavernous landscape. Within the cartwheel's brilliant band, the combined fury of stellar winds and supernova explosions does not just add light. It carves out immense voids in the very fabric of the interstellar medium. These are supershells and superbubbles, titanic cavities blown in the galaxy's gas, each hundreds or even thousands of light years across. Picture the ring not as a solid wall of stars, but as a cosmic sponge or a piece of galactic Swiss cheese riddled with overlapping, hollowed-out spheres. Each one begins with a cluster of the most massive stars. In their short lives, these giants blast out fierce winds of charged particles, like a constant multimillion-mile-per-hour hurricane radiating from each star. These winds begin to push against the surrounding gas, slowly inflating a bubble. Then, one by one, the stars reach the end of their lives and detonate. Each supernova injects the energy of a billion suns into that growing cavity, like a series of depth charges going off inside an already expanding balloon. The combined force of these sequential explosions can merge individual bubbles into a single, colossal supershell, a hollowed-out region of hot, thin gas surrounded by a dense, compressed wall of cooler material. The Cartwheel's ring, with its concentrated starburst, is likely a labyrinth of these structures, a frothing sea where new bubbles are constantly being blown inside and alongside older ones. This porous architecture fundamentally reshapes the ring's ecology. Those dense, cool walls surrounding each supershell are where the next act of creation begins. The shockwaves from the expanding bubbles slam into this collected material, compressing it just as the original galactic collision did, but on a smaller, more localized scale. This can trigger secondary waves of star formation, not from the main galactic shockwave, but from the aftermath of stellar death. New star clusters ignite along the inner surfaces of these gigantic bubbles, lining the caverns with fresh blue light. It is a feedback loop of breathtaking scale where one generation of stars in dying clears the space and prepares the fuel for the next. The ring becomes a self-propagating engine, its structure evolving from a simple wave into a complex, bubbly foam. This Swiss cheese structure also changes how energy moves through the galaxy. The hot gas inside these superbubbles can eventually break through the shell, venting out into the galactic halo or into adjacent cavities. This creates chimneys and tunnels, pathways that allow the intense radiation and heated particles from the stellar nursery to escape, potentially influencing regions far from where they were born. The Cartwheel's beautiful ring, therefore, is not a smooth disk of creation. It is a dynamic, evolving foam, sculpted by the very stars it creates, a testament to how destruction and construction are forever linked in the cycle of a galaxy's life. The porous, foamy structure of the ring hides a deeper chemical secret in its cold, dark caverns. Astronomers listen for the faint radio whisper of carbon monoxide, a simple molecule that acts as the universe's most reliable tracer for the coldest, densest gas clouds, the very raw material from which stars are born. Yet in the Cartwheel, this molecular map sometimes tells a story that doesn't quite match the brilliant light show. There are pockets where the carbon monoxide signal is strong, indicating a rich reservoir of star-forming fuel, but where few young stars have actually ignited. This mismatch is a profound clue to the galaxy's inner workings. One possibility is that we are looking at a stockpile, a cache of gas that has been gathered and compressed by the expanding ring, but has not yet crossed the critical threshold of collapse. It is fuel waiting for the spark, a stellar nursery under construction but not yet open for business. The time delay between gas compression and star formation can be millions of years, so these anomalous clouds could be a snapshot of the future, showing us where the next wave of blue giants will blaze to life long after our own civilization has passed. But there is another, more violent interpretation. These carbon monoxide-rich star-poor regions might be crime scenes where star formation is being actively suppressed. Imagine a dense cloud beginning to coalesce under its own gravity, starting the delicate process of making stars. Then, from a nearby cluster of massive stars just a few light-years away, a hurricane of ultraviolet radiation and charged particles slams into it. This fierce stellar feedback can heat the gas, tear apart the fragile molecular structures, and blast away the cloud's outer layers. The gas might remain dense enough to emit a strong carbon monoxide signal, but the turbulent energy injected into it prevents it from cooling and fragmenting into stellar seeds. It is a cosmic battle between gravity and radiation, where the furious energy from one generation of stars stifles the birth of the next. These anomalous pockets reveal the ring as a dynamic battlefield, not a serene assembly line. They are the contested frontiers where the galaxy's past and future are locked in a silent struggle, and the carbon monoxide map is the scorecard, showing us where gravity is winning and where the fury of newborn suns holds creation at bay. Our eyes are only seeing the calm after the storm. The Cartwheel's brilliant blue ring is a softened echo of its true ferocity, a portrait painted in the gentle light that our human vision can perceive. To see the galaxy's raw, unshielded violence, you must look with different eyes in the searing glare of ultraviolet light. Here, the beautiful ring transforms into a blistering circle of fire, a coronet of pure, high-energy fury. Ultraviolet radiation is the signature of the universe's most extreme stellar youth, emitted almost exclusively by the surfaces of the hottest, most massive stars, those that burn with a temperature of tens of thousands of degrees. These are stars that lie on the edge, destined to explode in just a few million years, and their ultraviolet light is so intense it is almost entirely absorbed by the very dust clouds that birthed them, rarely escaping into the visible spectrum. This makes ultraviolet telescopes like a special filter that removes all but the newest, most violent stellar neighborhoods. When we apply this filter to the Cartwheel, the diffuse glow of older stars and the soft light of smaller suns simply vanish. What remains is a stark, skeletal map of the propagating wave's very cutting edge. The ultraviolet ring is not a smooth band. It is a string of brilliant, searing knots, each one a superstar cluster in its infancy. These are the sites where the shockwave's compression was most effective just a few million years ago, where thousands of monstrous blue giants ignited almost simultaneously, flooding their surroundings with a radiation so harsh it sterilizes space for light years around. This ultraviolet map shows us the wave's progress with surgical precision, revealing which segments of the ring are currently in the throes of the most violent birth and which have already passed that peak of intensity. The fire is not uniform. It flickers and flares along the ring's circumference, telling a story of a shock wave encountering pockets of resistance and reservoirs of plenty in the galactic gas. To see the Cartwheel in ultraviolet, it is to witness the moment of stellar ignition itself, to look past the beauty and directly into the forge where galactic futures are hammered out in blinding, searing heat. These blue blobs are not just dense star clusters, they are potential new worlds in the making. The theory of tidal dwarf galaxies takes the violence of a collision and turns it into a story of cosmic genesis. When galaxies collide and stretch out their immense tidal tails, they don't just spray out individual stars. They can eject enormous, cohesive clouds of gas and dust, some containing the mass of a small galaxy itself. If such a cloud is dense enough and contains sufficient mass, a remarkable thing happens. Its own self-gravity can overcome the tidal forces trying to tear it apart from the parent galaxy. This cloud then begins to collapse in on itself, independent of the system that spawned it. Within this isolated cocoon, star formation ignites, and a new dwarf galaxy is born from pure wreckage. This is not a galaxy that existed before the crash. It is a phoenix rising from the galactic ashes. For the blue blobs in the Cartwheel's ring, the question is whether they meet the strict criteria to earn this title. First, they need enough mass to hold themselves together against the immense gravitational pull of the massive Cartwheel just next door. Estimates suggest some of these blobs do indeed contain billions of solar masses, which is on par with many known dwarf galaxies. Second, they need a healthy reservoir of cold gas, the fuel for future generations of stars. Observations show these blobs are rich in hydrogen and dust, indicating they are not just clusters of stars that will soon burn out, but systems with a deep fuel tank for a long stellar future. The most critical test, however, is dynamics. Are the stars and gas within each blob moving in orbits bound primarily to each other? or are they still just loosely associated debris being dragged along by the cartwheel's immense gravity? This is where the detective work gets difficult. The blobs are so close and so young that distinguishing true, independent rotation from mere tidal streaming is a monumental challenge. Some might be genuine infant galaxies already on their path to independence. Others could be in a transient state, massive enough to start the process of self-gravitation, but ultimately destined to be torn apart and pulled back into the main ring over the next few 100 million years. We could be witnessing a cosmic sorting process where the collision creates dozens of potential new islands, and only the heaviest and most resilient will survive to become true companions. The Cartwheel's ring, therefore, is more than a stellar nursery. It is a galactic maternity ward where the chaos of a single impact is actively forging entirely new futures, testing in real time which clumps of wreckage have what it takes to become a universe of their own. This forensic astronomy extends beyond the Cartwheel's beautiful wreckage to the suspect galaxies themselves. By dissecting the light from the two companion galaxies, G1 and G2, with the precision of a cosmic prism, astronomers can perform a chemical autopsy. Every star, every wisp of gas in a galaxy carries a specific chemical fingerprint, a unique blend of elements forged in stellar cores and scattered by supernova explosions over billions of years. This composition is a galaxy's birth certificate and its life story. If the Cartwheel's ring is a stew made from the ingredients of two separate galaxies, then we should be able to taste the individual flavors in the final dish and trace them back to their original pots. The key is to look for subtle differences in metallicity, the abundance of elements heavier than hydrogen and helium between the companions and the ring. Imagine two neighboring families, each with their own distinct recipe for a spice blend passed down through generations. If you find a new pot of that blend at the scene of a party, you could analyze it and say, this has the high cinnamon signature of the Smith family and the distinct cardamom notes of the Jones family. In galactic terms, one galaxy might have a higher ratio of oxygen to iron, a signature of many rapid supernovae from massive stars. Another might show an overabundance of elements like europium, which are forged primarily in the collisions of neutron stars, a rarer and slower process. By meticulously measuring these ratios in the companion galaxies and then comparing them to different parts of the Cartwheel's ring, scientists could perform a cosmic lineage test. They could ask, does the chemical makeup of the blue blobs at the ring's edge more closely match the ragged, gas-stripped G2? Does the metallicity of the older, fainter stars in the inner regions align more with the composition of the larger G1, suggesting it was part of the original system? This is not just about identifying the bullet, G2, but about reconstructing the entire messy exchange. The collision would have mixed materials from all three bodies in a chaotic swirl. Some gas from the Cartwheel's original disk might have been flung out and captured by the intruder. Some pristine gas from the companions might now be fueling the Cartwheel's starburst. A detailed chemical map would let us trace these flows. If a segment of the ring shows a chemical signature utterly alien to the current Cartwheel core, but a perfect match for G2, it would be direct evidence that this part of the ring was built almost entirely from the intruder's stolen substance. This forensic work turns the beautiful image into a three-dimensional crime scene reconstruction, allowing us to watch the collision not as a single instant, but as a process of grafting and fusion, where the very elements that make up stars and planets were exchanged between galaxies, writing their shared history into the atomic structure of every new sun born in the ring's brilliant fire. That chemical map is a snapshot of a single moment, but the Cartwheel's true nature is written in flickering light. This galaxy is not a static portrait. It is a living cinema of cosmic violence, and to watch its film requires a special kind of patience. Time-domain astronomy is the art of staring, of meticulously comparing images of the same patch of sky taken weeks, months, or years apart, searching for the telltale blink of something that has changed. For transient hunters, astronomers who specialize in these cosmic flashes, the Cartwheel Galaxy is a potential treasure trove of the rare and the explosive, a dynamic stage where the script is written in sudden, brilliant eruptions. Imagine monitoring that brilliant blue ring over years. Most of those millions of stars will shine with a steady, unwavering light, but scattered among them are ticking time bombs and sudden cataclysms, events that flare into existence and then fade, sometimes forever. One of the most dramatic could be the eruption of a luminous blue variable star. These are among the most massive and unstable stars in the universe, true stellar behemoths that live on the edge of self-destruction. They don't just shine, they convulse. Every few decades or centuries, a luminous blue variable can undergo a monstrous outburst, violently ejecting a shell of its own outer layers into space. For a brief period, it can become millions of times brighter, outshining entire star clusters before settling back down. Catching one of these eruptions in the act, especially in a galaxy so far away, would be a monumental discovery, offering a front-row seat to the final, turbulent centuries of a star hundreds of times more massive than our Sun. But the flashes would not stop there. The ring is also a breeding ground for binary star systems, pairs of stars locked in a gravitational embrace. Among these, we could witness the sudden flare of a nova. This happens when a dense, Earth-sized white dwarf star steals hydrogen-rich gas from its companion. That gas accumulates on the white dwarf's incredibly hot surface until, like a cosmic pressure cooker, it triggers a runaway thermonuclear explosion. The star can brighten by a factor of 50,000 in a single day, a brilliant beacon that slowly fades over weeks. Unlike a supernova, the white dwarf survives this ordeal, and the process can repeat every few thousand years as it steals more fuel. Spotting these nova in the Cartwheel would help astronomers count these binary systems and understand the late-stage evolution of stars in this extreme environment. Then there are the events born from true stellar annihilation, tidal disruption events. While the galaxy's central black hole may be quiet now, smaller, stellar mass black holes almost certainly lurk within the ring. If one of these black holes, perhaps in a microquasar system, ventures too close to a normal star, its immense tidal forces can stretch and rip that star apart in a process called spaghettification. As the stellar debris swirls into a doomed disk around the black hole, it heats to millions of degrees, unleashing a final, brilliant flash of X-rays and visible light that can last for months. Catching the afterglow of such an event in the Cartwheel would be a direct observation of a star's final moments, a chance to study the feeding habits of these smaller monsters in a stellar nursery. Each of these transients is a fleeting cosmic signature, a single frame in the galaxy's long-running film. Monitoring the Cartwheel over time transforms it from a beautiful object into a dynamic laboratory. Every flicker, every new point of light that appears and vanishes, is a data point in the life cycle of stars, a clue to the hidden populations of binaries and black holes, and a reminder that even in a structure hundreds of millions of years old, the most dramatic stories often unfold in the blink of a cosmic eye. The invisible architecture of dark matter is the true stage upon which this galactic drama plays out. Earlier we touched on the ghostly halo, but its role is far more active than just providing hidden mass. The Cartwheel's beautiful rotation and the frantic dance of its companion galaxies are not governed by the stars we see, but by the immense, unseen gravitational well of its dark matter halo, a sphere of mystery that may extend 10 times farther than the brilliant ring itself. This halo is the cosmic glue that holds the entire system together, especially after a collision that should have torn it apart. Think of it like this: the visible galaxy is a chandelier, a beautiful but fragile structure of glass and light. The dark matter halo is the massive, unseen ceiling beam from which that chandelier is suspended. The collision was like swinging a wrecking ball through the chandelier. The glass shattered and rearranged into a new ring shape, but the beam above, the dark matter, simply shuddered and remained largely in place. This is the core prediction of the cold dark matter model, which posits that dark matter particles interact only through gravity, not through the electromagnetic force that causes normal matter to crash and stick. During the high-speed piercing collision, the dark matter halos of the two galaxies should have passed right through each other like ghosts, barely noticing the impact while their gas and stars slammed together violently. If this model is correct, then today, the peak density of the Cartwheel's dark matter halo should not be centered on the brilliant ring of young stars. It should be offset, lagging behind, or perhaps still aligned with the galaxy's original, now dispersed central bulge. We can search for this displacement by studying two things with exquisite care. First, the precise rotation curve of the cartwheel itself. By mapping the speeds of hydrogen gas clouds at different distances from the center, we can weigh the gravitational pull at each point. If the rotation speeds remain high far outside the visible ring, it means a huge amount of mass, the dark halo, is still exerting its pull from a wider, perhaps displaced region. Second, we can study the orbits of the companion galaxies G1 and G2. Their paths are not random, they are governed by the total mass of the entire cartwheel system, dark matter included. By tracking their motions over time, we can reconstruct the shape and concentration of the invisible gravitational field they are swimming through. A displaced dark matter halo would tug on them in subtly different ways than a perfectly centered one. This makes the cartwheel a crucial test bed. If we find clear evidence that the dark matter was indeed separated from the visible wreckage, it powerfully confirms the cold dark matter model. But what if the data shows the dark matter halo still snugly wrapped around the visible ring? That would be a shock. It would suggest that dark matter might have some other unexpected property, perhaps a faint ability to interact with itself or with normal matter beyond gravity, causing it to get dragged along with the colliding gas. Such a finding would open the door to alternative theories, like self-interacting dark matter or even modifications to our understanding of gravity itself. The cartwheel, in its beautiful chaos, offers us a rare controlled experiment. Its perfect ring is the known outcome for normal matter. Any gravitational anomaly is the signature of the unknown, a chance to weigh a ghost and finally understand the invisible skeleton that shapes not just this galaxy, but every galaxy in the cosmos. The debris flung from the collision creates more than just ghostly tales. It builds entirely new homes for stars in the emptiness between galaxies. This is the phenomenon of intergalactic star formation, where stellar nurseries ignite not within the safe confines of a galactic disk, but out in the desolate wilderness, within the bridges of gas and dust that connect the cartwheel to its companions. These would be orphan star clusters, born in the tidal debris streams and destined to live their entire lives in the void, untethered to any major galaxy. The concept challenges our basic idea of where stars belong. We think of galaxies as islands of light in a dark ocean, but here, the violent splash of the collision itself can toss up enough material to form temporary floating islands. For this to happen, the gas in the tidal tails must be incredibly dense and massive. The gravitational shock of the collision doesn't just stretch the material, it can also compress certain pockets within the streaming debris. If a cloud of gas becomes dense enough and cool enough, its own self-gravity can take over, pulling it together to form stars even as it drifts further into the abyss. The question for astronomers is whether we see the evidence. Scouring the faint tidal tails of the cartwheel system for the pinpoint blue light of young star clusters is a monumental challenge. These clusters would be incredibly faint, their light diluted across vast distances and competing with the glow of the main galaxies, but there are tantalizing hints. Some observations of the system's faint arcs reveal subtle knots of bluer light, slight concentrations that could be the signatures of stellar nurseries operating far from home. These would not be grand spirals, but likely compact, globular-like clusters containing perhaps millions of stars. Their lives would be strange and isolated. Without the protective disk of a galaxy, they would be exposed to the harsh radiation of intergalactic space. They would have no reservoir of fresh gas to draw from for future generations, so their star formation would be a single, brief burst before fading into a cluster of old red stars. If confirmed, these intergalactic clusters would be direct descendants of the crash, celestial refugees born from the wreckage and set adrift. Their very existence would prove that a galaxy's influence doesn't end at its visible edge, that its creative power can spill out into the void, seeding the darkness with lonely sparks born from pure chaos. The Cartwheel's true portrait is not a single photograph, but a layered mosaic, a composite assembled from many different kinds of light. Each wavelength our telescopes capture reveals a separate chapter of the story, a hidden layer of reality invisible to the others. To understand this galaxy, you must look through many different eyes and piece together a puzzle where the image only makes sense when every piece is in its place. The iconic view from the Hubble Space Telescope gives us the optical masterpiece, the stunning blues and golds of the ring and its ghostly spokes. This is the galaxy's skin, the light emitted directly by its stars. But it is only the surface. To see the violence beneath that beauty, we turn to the Chandra X-ray Observatory. Chandra's gaze cuts through the optical glow and reveals the searing, pinpoint beacons of the ultraluminous X-ray sources, those potential black holes and neutron stars feeding at a furious pace. It shows us the superheated gas from countless supernovae, a diffuse, multimillion-degree plasma that fills the ring like a fever. This is the galaxy's high-energy nervous system, the sites of its most extreme and destructive processes. Then, to see what the dust hides, we shift to the infrared. The Spitzer Space Telescope, and now the James Webb Space Telescope, peer through the thick cosmic soot that obscures the optical view. In infrared light, the dark lanes in Hubble's image blaze with warmth. We see the fierce glow of heated dust grains, and we witness star formation happening in the shadows, revealing that the stellar baby boom is even more widespread than the blue light suggested. This layer shows us the fuel and the furnace, the raw materials being consumed and the thermal aftermath of creation. Finally, radio telescopes like the Very Large Array listen to the galaxy's deeper song. They map the cold hydrogen gas, the primordial fuel reservoir that doesn't glow in visible light at all. This reveals the broad, offset halo of raw material, showing us where the next wave of stars might form. Radio waves also trace the frenetic spiraling of electrons along tangled magnetic fields, painting a picture of the invisible force that shapes the movement of charged particles and helps contain the galaxy's chaotic energy. Alone, each image is a stunning but incomplete truth. Hubble shows the beauty but misses the violence. Chandra sees the violence but not the cold fuel. Webb reveals the hidden heat but not the magnetic skeleton. Only when we layer them all together, aligning the optical ring with the X-ray beacons, the infrared glow, and the radio map of gas, does the full, multidimensional reality of the Cartwheel snap into focus. We see that a brilliant blue star cluster is often ringed by hot X-ray gas and sits atop a mound of warm dust, all embedded in a vast cloud of cold hydrogen laced with magnetic force. This multi-wavelength mosaic transforms a beautiful picture into a rich physical narrative, proving that to understand a galaxy's soul, you must learn to see in every color of the cosmic rainbow. That multi-wavelength portrait is a symphony of light, but the true sound of the collision is a vibration in the fabric of reality itself. We cannot hear it in space, for sound needs a medium to travel, and the cosmic void is a perfect silence. Yet, if we could translate the event into a form our senses could grasp, the collision that birthed the Cartwheel would have roared. This conceptual sound would not be carried by air, but by the stretching and squeezing of spacetime, a phenomenon we call gravitational waves. When the smaller galaxy's core punched through the heart of the cartwheel, it was not just stars and gas that were thrown into chaos. The incredible masses involved, billions of suns swinging past each other at fantastic speeds, would have warped the very geometry of the universe around them. Imagine two immense weights, each the mass of a galactic core, spinning around each other in a final, deadly dance before merging. As they spiraled inward, their motion would have sent powerful ripples outward through the cosmos, traveling at the speed of light. These ripples are gravitational waves, literal distortions in the fabric of space-time, like the waves that spread when you drop a stone into a still pond, but in all three dimensions. If our ears could somehow detect these ripples, what would we hear? It would not be a crash or a bang. The frequency would be incredibly low, a deep, resonant hum that built in intensity over millions of years as the galaxies drew closer, culminating in a final, rising chirp at the moment of the core's piercing impact. The pitch of this hum is determined by the scale of the event. The more massive the objects and the larger their orbit, the lower the frequency. A collision of entire galactic cores would produce a hum so deep it would be far below the range of human hearing, a bass note with a wavelength measured in years. Current observatories like LIGO are tuned to hear the much higher frequency chirps of merging stellar mass black holes and neutron stars. The monumental, slow-motion collision that created the cartwheel is a different kind of music entirely, one that would require a galaxy-sized detector to hear. But thinking about it sonically gives us a visceral feel for the energy involved. That deep, conceptual hum represents the conversion of an almost unimaginable amount of mass into pure vibrational energy, shaking the cosmos itself. It is the universe's own way of ringing a bell to mark the catastrophic birth of a celestial wonder, a silent song of creation that has been traveling outward for 500 million years, carrying the news of the cartwheel's violent origin to the farthest reaches of space. The brilliant ring is not a permanent crown but a fleeting, fiery bloom. Its future is written in the dwindling gas and the aging light of its own stars. Computer simulations allow us to fast-forward the cosmic clock by billions of years, projecting the fate of this galactic bullseye. The story begins with exhaustion. That spectacular wave of star formation, the very thing that makes the ring blaze so blue, is also its undoing. The process is voraciously consuming the cold hydrogen gas that fuels it. Within a few 100 million years, perhaps 1 billion at most, the ring will have burned through the majority of its pristine fuel reservoir. The era of frantic starbirth will come to an end. Without new massive blue stars to replace them, the color of the ring will fundamentally change. The hottest, brightest giants will be the first to die in supernova, and as the stellar population ages, the dominant light will shift from fierce blue to a softer yellow, and eventually to a dull, ruddy red. The ring will transform from a neon sign of creation into a somber circle of ancient, long-lived red dwarf stars and the fading embers of stellar giants. But what of its shape? Will it hold together? The simulations suggest a slow, gravitational unraveling. The initial clean shockwave will dissipate as it runs out of gas to compress. Without that propagating pressure front to maintain its sharp edge, the ring's structure will begin to blur. The gravitational pull of the galaxy's inner regions and the dark matter halo will start to reassert their influence. Stars in the ring, each on their own slightly perturbed orbit, will begin to drift. The perfect bullseye will slowly smear. Some simulations show it fragmenting into distinct, massive star clusters that orbit like pearls on a string, which then themselves slowly disperse. Others suggest the ring will gradually fall back inward, its material settling into a more chaotic, thickened disk. The beautiful, thin ring is a product of a specific, violent impulse. Once that impulse fades, the galaxy's gravity will work to erase it, tugging the structure toward a more relaxed, equilibrium state, likely a featureless, puffy, elliptical galaxy or a very disturbed, amorphous spiral. The final act may involve the return of the intruder, Remember, Galaxy G2 is still gravitationally bound and will eventually fall back in. That second, slower merger will stir the pot once more, thoroughly mixing any remaining ring structure into a smooth stellar halo. The Cartwheel's magnificent form is therefore a temporary masterpiece, a brilliant but unsustainable flash in the pan of cosmic time. We are witnessing it in its brief, violent prime, a phase that will end long before the galaxy itself grows old. The Cartwheel's violent present is a key to the universe's violent past. This brilliant ring galaxy, for all its strangeness, might be the closest thing we have to a time machine, offering a clear, nearby blueprint for understanding the most distant and ancient galaxies in the cosmos. We call these faraway systems high redshift galaxies, their light stretched and reddened by the expansion of the universe over billions of years. To our most powerful telescopes, they appear as faint, fuzzy blobs, their details lost to unimaginable distance and time. Yet within those blurry smudges, astronomers often detect the same telltale signatures we see so clearly in the Cartwheel: fierce bursts of ultraviolet light, overwhelming infrared glows from dust, and the radio hum of frantic star formation. The early universe was a riotous construction site, a place where galaxies were smaller, gas was abundant, and catastrophic collisions were a regular feature of cosmic life. Giant, graceful spirals like our Milky Way were rare, the calm after a long period of stormy mergers. In that chaotic era, galaxies likely looked a lot less like perfect pinwheels and a lot more like the Cartwheel does right now, messy, asymmetric, and blazing with the blue fire of newborn stars. By studying the Cartwheel in exquisite detail right here in our cosmic neighborhood, we are essentially reading the instruction manual for that distant epoch. We can take the fuzzy image of a high redshift galaxy and ask, does its light profile match what we see when we blur the Cartwheel to the same resolution? Does its spectrum show the same intense emission lines from ionized gas that we see in the Cartwheel's ring, a signature of fierce ultraviolet radiation from massive stars? When we detect a galaxy at the edge of observable time that seems to be forming stars at a rate of hundreds per year, we can look to the Cartwheel to understand the mechanics of such a starburst. How is the gas compressed? What role do mergers play? How does the energy from those stars then regulate or quench further formation? The Cartwheel provides the answers in high definition. It shows us the precise chain of events, from a piercing collision to a propagating shockwave to a ring of intense creation. It demonstrates how a single event can funnel gas and trigger star formation on a galactic scale. This local template allows astronomers to build better computer models of the early universe. They can input the physics observed in the Cartwheel, the efficiency of shockwave compression, the rate of supernova feedback, the behavior of magnetic fields in the chaos, and then run those models to see if they can reproduce the populations of faint, distant blobs we actually see. In this way, the Cartwheel is more than a celestial oddity, it is a Rosetta Stone. It translates the faint, cryptic signals from the cosmic dawn into a vivid narrative of creation, giving us a front-row seat to the violent, beautiful processes that built the first generations of galaxies and set the stage for everything that followed. But the Cartwheel is not sailing through a perfect void. It is moving at high speed through a ghostly ocean, the intergalactic medium. This is the thin, almost imperceptible soup of gas and dust that filaments the vast spaces between galaxies, a remnant of the universe's earliest days. For most galaxies, this medium is too diffused to matter, but the Cartwheel's velocity and its recent trauma might make this interaction a key part of its story. As the entire system speeds along, it could be plowing into this tenuous gas like a ship cutting through a calm sea. If the speed and density are just right, this would create a colossal bow shock, a standing wave of compressed and heated gas that wraps around the galaxy's leading edge. We cannot see this shock in visible light, but it might reveal itself as a faint, arc-shaped enhancement in radio or X-ray emission, a subtle pressure front millions of light years across. This bow shock would do more than just glow, it would act as a cosmic buffer. It could sweep up and compress the intergalactic gas, funneling it toward the galaxy and potentially providing a trickle of fresh fuel for future star formation, a slow accretion from the cosmic void. Conversely, that same shock could be stripping gas away. If the ram pressure from the impact is strong enough, it might be able to peel the most loosely bound hydrogen from the very outskirts of the cartwheel's own extended halo or from the delicate strands of its tidal tails. This would be a gentle but persistent erosion, a galactic wind slowly sanding away the furthest reaches of the wreckage. The tidal tails themselves, those faint streams of exiled stars and gas, become critical testing grounds for this idea. Are their outermost tips being swept back, shaped by this interstellar wind like smoke from a candle in a breeze? Or do we see evidence of new gas clumping along their length, material gathered from the medium as they sweep through it? The answer shapes the galaxy's ultimate fate. Is the cartwheel bleeding its remaining gas into the void, or is it slowly gathering new raw material from the cosmos to replenish what was lost in the collision? This quiet interaction with the invisible medium is a long-term battle between loss and gain, a subtle force that will, over billions of years, help decide whether this galaxy's brilliant ring is its final act of youth or merely the first chapter in a longer, more complex story of survival. Even our sharpest eyes have limits. For all its power, the Hubble Space Telescope sees the cartwheel's brilliant ring as a tapestry of blended light, where thousands of distant stars merge into a single glowing pixel. We can measure the collective color and brightness of these regions, but the individual stories are lost in the crowd. This blurring is the final frontier in our investigation, a fundamental barrier between us and the galaxy's most intimate secrets. But that barrier is about to shatter. A new era of resolution is dawning, led by the James Webb Space Telescope and the coming generation of colossal ground-based observatories with mirrors the size of small buildings. Their unprecedented power will perform a feat of cosmic microscopy, resolving the cartwheel's crowded neighborhood star by star for the very first time. This is not just a sharper picture, it is a scientific revolution. Imagine being able to study a bustling city, not from a satellite image showing blurred blocks of light, but from a vantage point where you can see every single person, every car, every window. That is the leap we are about to make. Instead of inferring the history of star formation from the blended glow of millions, we will be able to construct a true stellar census. We will pinpoint individual red giant stars, the ancient inhabitants from before the collision, and trace their specific motions to understand how the impact scattered them. We will identify the exact locations of the youngest, most massive blue stars, mapping the wave of creation with pinpoint accuracy to measure its speed and efficiency down to the scale of individual stellar nurseries. Most profoundly, we will be able to take the chemical fingerprint of single stars. By analyzing the light from one star at a time, Webb's infrared spectrographs can measure the precise abundance of elements like carbon, oxygen, and iron in its atmosphere. This allows us to do galactic archaeology at its finest. A star with high levels of elements forged only in the slow death of old stars tells us it formed from gas enriched by many previous generations. A star with a purer, more primordial composition might be a true first-generation child of the collision, born from gas that had never been part of a star before. By building a chemical map star by star, we can reconstruct the mixing of materials from the two original galaxies with forensic detail. Did the intruder galaxy contribute a distinct chemical flavor to one specific arc of the ring? Are there pockets of stars with identical chemistry, suggesting they all formed from the same shredded gas cloud? This granular view will answer the unresolved questions of stellar populations, finally telling us if the old stars are truly missing or merely hidden, and revealing the complete life history of this galactic wreck, written in the atmosphere of every sun we can now see as an individual point of light. The blur will lift, and the cartwheel's millions of stories will begin to be told, one brilliant star at a time. This perfect ring forces us to confront a staggering truth of cosmic timing. How lucky are we, really, to see this? The Cartwheel Galaxy is a statistical miracle, a fleeting masterpiece we just happened to catch in the brief, brilliant act of its existence. Galactic collisions themselves are not rare. Across the vast universe, galaxies are constantly merging, drawn together by gravity in a slow, cosmic dance. But the vast majority of these encounters are glancing blows or drawn-out mergers that warp and twist galaxies into messy, irregular shapes. They do not create perfect bullseyes. For a ring galaxy like the Cartwheel to form, the conditions must be exquisitely precise. The smaller galaxy must strike the larger one almost dead center, a piercing impact rather than a sideswipe. The angle must be nearly perpendicular, and the speed must be high enough to create a clean shockwave, but not so high that it completely shreds the target. It is the celestial equivalent of threading a needle with a bullet from a distance of millions of light years. Even among known ring galaxies, the Cartwheel stands out for its symmetry and clarity. Many others are lopsided or fragmentary. This one is a textbook diagram brought to life, which suggests its formation was a particularly clean and violent example of an already rare event. But the rarity does not end with the collision itself. The spectacular phase we are witnessing, the brilliant blue ring, is astonishingly brief on cosmic timescales. That furious starburst, the defining feature that makes the Cartwheel so stunning, lasts for only a few 100 million years. To put that in perspective, our own sun has been shining for about 4.6 billion years, and the universe itself is nearly 14 billion years old. The Cartwheel's ring phase is a blink, a single flashbulb pop in a long, dark cosmic night. We are seeing it roughly 500 million years after the impact, which means we have caught it perhaps halfway through its prime. In another few 100 million years, its fuel will be exhausted, its blue giants will have died, and the ring will begin to fade and blur, losing its iconic shape over the ensuing billions of years. Our existence as a technological civilization capable of pointing telescopes at this galaxy aligns almost perfectly with this brief window of celestial spectacle. If human astronomers had emerged just a billion years earlier or a billion years later, the Cartwheel would have looked completely different, a faint, messy smudge without its defining ring. This perfect alignment of our time and its time is a profound reminder of our place in a dynamic, evolving cosmos. We are not passive observers of a static universe, but time travelers granted a front-row seat to one of its most violent and beautiful short-lived performances, a show whose run is almost impossibly short and whose next act is the slow fading of its brilliant light. Its perfect form transcends the sterile data of astronomy to touch something deeper in the human spirit. The Cartwheel Galaxy is more than a scientific specimen. It is a profound aesthetic object, a cosmic icon whose image has ignited imaginations far beyond the observatory. Its stark, symmetrical beauty makes it an almost irresistible subject, a masterpiece of natural geometry that feels both alien and strangely familiar. You will find its likeness everywhere, from the covers of popular science magazines to the breathtaking backdrops of documentary films and the vivid murals in planetarium domes. It has become a visual shorthand for the grandeur and mystery of the universe itself, a gateway object that draws people into the story of astronomy. Why does this particular galaxy resonate so powerfully? Its structure is instantly legible. Unlike the messy whirl of a typical spiral or the fuzzy blob of an elliptical, the Cartwheel presents a clear, almost symbolic form, a bullseye that our brains immediately recognize and find satisfying. It looks like something we made, a mandala or a sacred wheel, yet its scale is utterly inhuman. This tension between the familiar and the incomprehensible is the source of its artistic power. It allows artists and filmmakers to use it not just as scenery but as a narrative device. In science fiction, its ring might be portrayed as an ancient megastructure, a cosmic highway, or the scar of a forgotten war. For visual artists, its palette of brilliant blues against the dark dust lanes and golden core provides a dramatic, ready-made composition that speaks of creation and destruction in a single frame. It serves as a bridge, transforming the abstract concept of a galactic collision into a single, stunning, and unforgettable picture. This visual impact has a profound educational purpose. Before a presenter explains a single equation about gravitational shockwaves or propagating star formation, they show the image, and in that moment, the audience is hooked. The beauty disarms skepticism and fuels curiosity. It answers the unspoken question of why we should care about events 500 million light-years away, because we are wired to respond to beauty and pattern. The Cartwheel Galaxy makes the violent, chaotic processes of the cosmos tangible. It helps people visualize the unseeable force of gravity as a sculptor and the slow march of time as an artist. It turns data into drama. By becoming a staple of our visual culture, it performs a vital, often overlooked function. It popularizes not just facts, but a feeling, a sense of wonder that is the true foundation of scientific inquiry. It reminds us that the universe is not just a machine to be understood, but a gallery of unimaginable splendor, and sometimes the most violent events create the most breathtaking art. The stunning clarity of its image masks a fundamental uncertainty, one that underpins every calculation we make about this cosmic wreck. How far away is the Cartwheel Galaxy, really? This is not a trivial question of cosmic geography. It is the foundation of all other truths we try to discern. The distance to any galaxy is the master key that unlocks its physical reality. Get the distance wrong, and every other measurement, from its true size to the ferocity of its starburst, becomes a house of cards built on a shaky guess. For the Cartwheel, pinpointing this number has been a persistent and surprisingly difficult challenge, a puzzle where different methods whisper different answers. The most straightforward method uses the cosmic expansion itself, the redshift of its light. As the universe expands, it stretches the light waves from distant galaxies, shifting them toward the red end of the spectrum. Measure the redshift and you can calculate a distance, but this method relies on our model of the universe's expansion rate, which itself has uncertainties. For the Cartwheel, redshift places it roughly 500 million light-years away, but that number has a significant margin of error, a fuzzy zone of perhaps tens of millions of light-years on either side. To get a more precise, independent measurement, astronomers turn to cosmic mile markers within the galaxy itself, Cepheid variable stars. These are pulsating stars whose intrinsic brightness is directly tied to the rhythm of their pulsations. Measure the period of their brightening and dimming, and you know how luminous they truly are. Compare that known luminosity to how faint they appear from Earth, and you can calculate distance with remarkable precision. This is the gold standard for measuring distances to nearby galaxies, but for the Cartwheel there is a catch. Its distance pushes the limits of this technique. Cepheids are brilliant, but at 500 million light-years, they are incredibly faint pinpricks of light, buried in the galaxy's crowded, dusty ring. Distinguishing them from other stars and accurately measuring their pulsations requires the absolute sharpest eyes in the cosmos, like the Hubble and now the James Webb Space Telescopes. Even then, dust is the enemy. If a Cepheid is hidden behind a veil of the Cartwheel's own cosmic soot, it will appear dimmer than it really is, tricking us into thinking the galaxy is farther away than it actually is. Correcting for this dust extinction is a complex and delicate art. So what is the current best estimate? After painstaking work, astronomers have converged on a distance of about 500 million light-years, but the precise figure is still debated. A difference of just 10%, 50 million light-years, might not sound like much on a cosmic scale, but it changes everything. If the galaxy is closer than we think, then it is physically smaller. That magnificent ring would be less colossal, and the total energy of the collision that created it would be recalculated downward. The masses of the galaxies involved would be smaller. Conversely, if it is farther away, the ring becomes even more monstrous, and the collision becomes an event of even more staggering violence. Every supernova we see there would have been more energetic, every ultraluminous X-ray source even more powerful. A more precise distance would finally lock in the scale of the catastrophe, turning our qualitative awe into hard, quantitative understanding. It would tell us definitively just how big the hammer was that struck this galactic anvil, and how far its brilliant ring of fire truly stretches across the void. That delicate balance between creation and destruction is the galaxy's own internal clock. Within the Cartwheel's brilliant ring, a fierce and fundamental battle is raging, a cycle of feedback that will ultimately decide how long this spectacular fire can burn. This is the cosmic principle of self-regulation, where star formation does not just happen, it triggers its own limits. The process begins with those dazzling blue giants. In their short, furious lives, they do more than just shine. They blast their surroundings with hurricane-force winds of charged particles, streams of energy that push against the surrounding gas like a stellar pressure washer. Then, after just a few million years, they die in titanic supernova explosions, each one a detonation with the force of 1 billion suns. These two forces, the winds and the blasts, are the primary agents of feedback. They inject a colossal amount of energy and turbulence back into the very interstellar medium that birthed them. This is where the battle turns inward. That injected energy has two opposing effects. Initially, it can be constructive. The shock wave from a supernova can slam into a nearby quiet cloud of gas, compressing it and triggering a new round of star formation, like a chain reaction of stellar birth. We see this in the ring's bubbly structure, where new clusters ignite on the shells of older ones. But on a larger scale and over time, the effect is overwhelmingly destructive. The combined fury of thousands of these events creates a hostile environment. All that turbulent energy heats the surrounding gas, preventing it from cooling down and condensing into new stars. The stellar winds and radiation pressure physically push the gas away, dispersing the raw materials and clearing out entire neighborhoods. It is as if the galaxy's stellar children, in their explosive adolescence, are tearing apart their own nursery to prevent more siblings from being born. In the Cartwheel, this feedback loop is operating at a truly galactic volume. The ring is not just a site of star formation, it is a pressure cooker. The intensity of the starburst means feedback is happening everywhere simultaneously at an almost unsustainable rate. This creates a fascinating question of scale and timing. Is the feedback localized, merely carving out bubbles within the ring while the overall wave of creation continues unabated? Or has the feedback already become so pervasive that it is now quenching the starburst from the inside out, effectively capping the ring's lifetime? The answer likely lies in the gas we cannot see forming stars. Those pockets of dense carbon monoxide with few young stars might be the smoking gun, regions where the gas is present but the feedback from adjacent stellar clusters has heated and disrupted it so violently that gravity cannot win. The galaxy is literally fighting itself, its left hand creating stars while its right hand tears apart the fuel for the next generation. This self-regulation means the Cartwheel's brilliant ring carries the seeds of its own end. The very violence that makes it so luminous ensures it cannot last. The starburst will continue only as long as the gas can cool and collapse faster than feedback can disperse it. Once the balance tips, once the collective fury of stellar winds and supernova overwhelms the ring's ability to gather and cool its gas, the great fire will begin to flicker and fade. The galaxy's breathtaking beauty is therefore a portrait of a system in a precarious and temporary equilibrium, a cosmic dance where every step of creation forces a step toward dissolution, and the lifetime of its greatest spectacle is being counted down by the very stars that define it. Amidst this stellar battlefield, a profound question emerges. Could planets, those cradles of potential life, form in the chaos of the Cartwheel's ring? The environment here is the antithesis of a quiet cosmic suburb. Planet formation is a delicate dance of dust and gravity, requiring patience and calm. Within the brilliant blue fire, those conditions seem impossible. The first enemy is radiation. The fierce ultraviolet light from thousands of massive stars is a constant, sterilizing flood. It can blast away the delicate atmospheres of infant worlds and vaporize the icy mantles of dust grains before they can ever stick together to form planetary building blocks. Next are the shockwaves. The relentless drumbeat of supernova and the gale-force stellar winds create a turbulent, churning medium. A fledgling protoplanetary disk, a swirling pancake of gas and dust around a young star, could be torn apart by a nearby explosion or stripped bare by a passing shockwave before planets ever coalesce. Finally, there is gravitational chaos. The dense packing of so many stars in the ring's massive clusters means close encounters are frequent. The gentle gravitational pull that herds dust into planets around a solitary star like our Sun could be catastrophically disrupted by a passing stellar neighbor, flinging forming worlds into deep space or plunging them into their host star. In such a maelstrom, the classic, orderly process of planet formation we understand from our own solar system seems doomed to fail, yet the universe is endlessly inventive. We must look to the ring's quieter frontiers, between the brilliant blue knots in the slightly older, more settled regions just behind the main wave of star formation. Conditions may be less hostile. Here, stars a few million years older have cleared some of the immediate chaos from their vicinity. Their protoplanetary disks, if they survived the initial fury, could now be entering a more stable phase where dust can gently coalesce into planetesimals and eventually worlds. Furthermore, the ring is not monolithic. Its evolution will continue. As the current starburst ages and the most massive stars disappear, the radiation field will drop precipitously. The supernova rate will slow from a constant roar to an occasional rumble. In this later, more quiescent epoch, still within the ring but billions of years after our current view, a second chance may arise. Stars of lower mass, the long-lived red dwarfs and sun-like stars that formed alongside the blue giants but outlast them, will remain. Around these quieter suns, in a calmer interstellar environment, the patient process of planet formation could begin in earnest, using the dust enriched by the deaths of the earlier giants. The Cartwheel might therefore host two entirely different generations of planets. The first, if any exist, would be survivors of an apocalyptic childhood, battered worlds forged in fire. The second would be latecomers born from the ashes in a time of relative peace. Finding either would be a revelation, proving that planet building is a resilient process, capable of persisting even in the aftermath of a galactic wreck. The Cartwheel's perfect form finds a strange twin in the distant cosmos. Far beyond its own ring of fire lies another celestial bullseye, Hoag's object, a galaxy so similar in appearance and yet so utterly different in its story that it forces us to question everything we think we know about ring formation. Side by side, they are a study in cosmic contrasts. The Cartwheel is a textbook case of violent creation, its history written in fleeing companions and tidal debris. Hoag's object is a pristine, isolated mystery. Its ring is a perfect circle of blue stars orbiting a bright, yellow central core, but there is no sign of a second galaxy, no visible intruder, no telltale tidal tails pointing to a recent collision. It floats in splendid, unsettling isolation. This absence of a culprit is the heart of its enigma. If no galaxy punched through its heart, what carved this perfect ring? The similarities are what make the differences so profound. Both galaxies display that stunning separation between an inner population of older stars and an outer ring of youthful blue clusters. Both are rare ring galaxies, but the Cartwheel's ring is a propagating wave, a dynamic frontier of ongoing starbirth. Hoag's ring appears more settled, a stable structure where star formation may have happened in a single ancient burst. Its core is not a faint, puffed-out ghost like the Cartwheels, but a compact, brilliant sphere of ancient suns, a classic central bulge that somehow coexists with a perfect ring without any connecting spokes. So how do you explain Hoag's object without a collision? Astronomers have proposed several quieter, more patient theories. One suggests a process of extreme resonance. Over billions of years, subtle gravitational instabilities within the galaxy's own disk could have slowly gathered gas into a stable ring at a specific distance from the center, where orbits naturally reinforce themselves. Another idea points to a long-finished act of galactic cannibalism, where a small dwarf galaxy was completely devoured so long ago that all evidence of the merger has smoothed away, leaving only the reshaped ring of captured gas as its tombstone. There is even a speculative possibility that Hoag's object is the result of a rare, head-on collision that occurred so far in the distant past, over 10 billion years ago, that the intruder galaxy has since merged entirely and the tidal debris has completely dissipated, leaving behind only this perfectly healed scar. Studying these two galaxies together is like comparing a fresh crime scene with a cold case. The cartwheel has blood on the floor and the murder weapon still in the room. Hoag's object is a body with a perfect, unexplained wound and no suspects in sight. By analyzing both, astronomers can test the limits of their theories. They can ask, does every ring require a violent impact, or can galaxies sculpt themselves into such perfect forms through slower, internal processes? The cartwheel shows us the mechanism in brutal, clear detail. Hoag's object challenges us to consider that the universe might have more than one way to draw a circle in the stars, and that some of its most beautiful mysteries are the ones with no witnesses at all. Our understanding of this galactic wreck is not built on photographs alone, but on billions of digital calculations. The cartwheel story is a cosmic puzzle, and the most powerful tool for solving it exists not on a mountaintop, but inside the humming banks of a supercomputer. This is the realm of numerical simulations, where astrophysicists can recreate the entire catastrophe, from first approach to final ring, in a virtual universe made of pure mathematics and silicon. They start with the raw ingredients, the estimated masses of the original spiral and its intruder, their vast reservoirs of gas and dark matter, and the laws of physics. Then they set them in motion. The screen becomes a digital laboratory, and time is compressed from 500 million years into a few days of processing. What emerges is breathtaking, a movie of a galaxy's destruction and rebirth. You watch as a small, dense speck representing the intruder galaxy flies across the void. It approaches the beautiful spiral disk, and then, with a silent, digital cataclysm, it punches straight through the glowing core. The effect is instantaneous and beautiful. A clean ripple of color, representing density, expands outward from the point of impact, racing through the virtual gas. And in its wake, a brilliant ring of new stars ignites, a perfect bullseye that looks uncannily like the real Cartwheel Galaxy hanging in space. But the simulation is more than just a pretty animation. It is a forensic tool. The initial run is a first guess. Scientists then begin the meticulous work of tweaking the parameters, the dials of the virtual universe. They adjust the impact angle by a few degrees. They change the relative speed of the collision. They modify the mass ratio between the two galaxies. With each adjustment, they run the simulation again, watching to see which combination of variables produces not just a ring, but the cartwheel's specific ring with its size, its symmetry, and even the faint hint of its spokes. It is a process of cosmic trial and error, a way of testing which historical scenario fits the evidence we see today. This turns the distant galaxy into a repeatable experiment. We cannot go back in time to watch the real collision, but we can rerun it 1,000 times in a supercomputer, exploring every possible variation. Did the intruder come from above or below the galactic plane? Was it slightly heavier or lighter than we think? The simulations tell us. When a particular set of parameters consistently produces a virtual galaxy that matches the Hubble image in exquisite detail, we can say with much greater confidence that this is likely how it happened. These digital recreations do more than confirm the broad story, they reveal the subtle physics. They show how the dark matter halo likely slid through the collision unaffected while the gas crashed and compressed. They illustrate how the shockwave propagates and why star formation erupts in a ring and not a filled-in disk. They even model the future, predicting how the ring will blur and fade over the coming eons. Without these numerical simulations, the cartwheel would remain a beautiful but static snapshot. With them, it becomes a dynamic story, a chapter of cosmic history we can unpack, rewind, and play forward, uncovering the fundamental laws that sculpt not just this one galaxy, but the evolution of the entire universe. That digital detective work reaches beyond the supercomputer and into the homes of millions. The story of the cartwheel and of galaxies like it is not written by professionals alone. It is a story co-authored by the public, by volunteers who have become the eyes of modern astronomy through projects like Galaxy Zoo. This online platform presented a simple, revolutionary idea: give people images of galaxies from massive digital sky surveys and ask them to do what the human brain does best: recognize patterns. Millions answered the call. With a few clicks, anyone could help classify spiral arms, identify merging systems, and flag the bizarre outliers that computers might miss. In this vast, collaborative effort, oddities like the cartwheel get a second, third, and 10,000th look. While it was originally discovered by professional astronomers, countless ring galaxies and other peculiar systems have since been found by these citizen scientists, their keen eyes spotting the subtle signatures of cosmic violence that automated algorithms might dismiss as noise. This is more than just crowdsourcing, it is a fundamental shift in how discovery happens. The scale of data in modern astronomy is staggering. Surveys like the Sloan Digital Sky Survey have imaged hundreds of millions of galaxies. No team of professional astronomers, no matter how large, could ever hope to visually inspect them all, but a global community of curious people can. They bring a diversity of perspective and a powerful capacity for pattern recognition that even the best artificial intelligence still struggles to match. When a volunteer tags an image as strange or beautiful or unclassifiable, it rises to the top for professional follow-up. A curious ring, a lopsided shape, a strange smudge of light. These amateur flags have led to the discovery of entirely new classes of objects and deepened our understanding of galactic evolution. The cartwheel itself has undoubtedly been seen and classified by thousands of Galaxy Zoo participants, each click contributing to a statistical understanding of how rare such perfect rings truly are. This public involvement demystifies the scientific process. It transforms cosmic discovery from a distant, elite activity into a shared human endeavor. A teacher in Berlin, a student in Tokyo, a retiree in Buenos Aires, they can all log on and in a few minutes contribute to the map of the universe. They become part of the story, their collective curiosity forming a net that catches the universe's strangest treasures. This collaboration reminds us that the drive to understand the cosmos is a universal human trait, and that the telescope in the digital age is an instrument we can all learn to point. The radiation that sculpts the ring also writes a death sentence for biology. Within that brilliant blue fire, the ultraviolet flux is so intense it would strip the atmosphere from any Earth-like world in moments, and the relentless particle bombardment from stellar winds and supernova would scour its surface to bare rock. For life as we conceive it, needing stability and chemical complexity, the cartwheel's ring in its current state is a galactic sterilization chamber. This forces us to expand our thinking across time, to ask not if life could survive the storm, but if it could have existed before the storm, or if it might emerge long after the storm has passed. The quieter past holds the first possibility. Before the smaller galaxy punched through its heart, the Cartwheel was likely a normal spiral, not unlike our own Milky Way. For billions of years, it would have hosted generations of stable, sun-like stars in its tranquil spiral arms. Around those stars, planets could have formed in calm protoplanetary disks, and on some of those worlds, the slow, patient chemistry of life may have begun. If a civilization arose on such a world, its sky would have been a beautiful, familiar tapestry of stars. Then, the cataclysm. The first sign might have been a subtle gravitational disturbance, a shifting of the familiar constellations over centuries. Then, as the intruder galaxy's core approached, the night sky would have begun to fill with a terrifying, growing light, a second galactic core blazing brighter than the moon. The final approach and piercing impact would have been a spectacle of unimaginable violence, visible in the daytime sky. The ensuing shockwave, propagating at a substantial fraction of the speed of light, would have taken tens of thousands of years to reach their world. When it did, it would have been an apocalypse. The wave of compressed gas might not have physically destroyed the planet, but the triggered burst of star formation in their immediate galactic neighborhood would have flooded their solar system with lethal radiation. Any surviving life would have been driven underground or into the deepest oceans, facing a long, grim fight for survival in a suddenly hostile cosmic environment. It is a haunting thought that the Cartwheel's beautiful ring might be the funeral pyre of civilizations we will never know, their histories erased by the very light that makes this galaxy so stunning to us. But time moves forward, and the future offers a different, more hopeful speculation. The current starburst is a short-lived fire. Within a billion years, the massive blue stars will be gone. The supernova rate will plummet from a constant roar to an occasional, distant echo. The radiation field will drop to levels comparable to quieter galaxies. What remains will be the long-lived stars, the red dwarfs and sun-like stars that formed in the ring but were overshadowed by their brilliant siblings. These stars will remain, along with any planets that managed to form in the brief, sheltered windows between cataclysms, or that coalesced later from the metal-rich debris. In this future, far more distant epoch, the Cartwheel's ring could become a haven. Its once lethal environment would have settled into a stable, if densely populated, stellar neighborhood. A planet orbiting a stable star in this older ring would have a breathtaking view, a band of countless suns arching across its sky, a permanent monument to the ancient violence that forged its home. The very elements needed for life, carbon, oxygen, iron, silicon, would be abundant, forged in the hearts of those early giants and scattered by their explosive deaths. Life, if it began then, would inherit a galaxy already enriched by its dramatic past. So while the Cartwheel today is a monument to cosmic violence, it may also be a cradle for the future, a place where the ashes of stellar giants become the soil for worlds yet unborn, and where the story of life against all odds might just be waiting for the fire to die down before it begins. The Cartwheel Galaxy is not just a spectacle, it is a singular, invaluable laboratory for extreme astrophysics. On Earth, we build particle colliders and fusion reactors to study matter under incredible conditions, but they are toys compared to the forces at work here. This galaxy offers a natural experiment on a cosmic scale, where the variables of mass, velocity, and gravity are set to levels we could never hope to achieve, allowing us to watch the universe's most fundamental processes play out in real time. Take collisional dynamics. We have theories and computer models for how galaxies interact, but they are based on assumptions. The Cartwheel is the cleanest, most observable result sheet from that exam. Its perfect ring and fleeing companion galaxy give us the before and after pictures in one frame, letting us test our simulations against a flawless, finished product. We can measure the exact outcome of a high-speed central impact and refine our understanding of how gravity sculpts matter on the largest scales. Then there are starburst triggers. We know dense gas makes stars, but the Cartwheel shows us the ignition mechanism with brutal clarity. It demonstrates how a single gravitational shockwave can convert an entire galactic disk into a stellar furnace, letting us measure the efficiency of this conversion, the rate of the star formation wave, and the ultimate limits of such a frenzy. It answers the question of just how much cosmic violence it takes to light up a galaxy. The mystery of its quiet central black hole is another critical experiment. Our models said the collision should have fed the monster, creating a brilliant quasar. The fact that it did not forces us to revise those models. Is there a time delay? Did the black hole already feast and then shut itself off? Or does the gas get funneled outward into the ring more efficiently than inward toward the core? The Cartwheel's silent heart is a failed prediction, and in science, a clear failure is often more valuable than a fuzzy success because it points directly to what we are missing. Even the evolution of magnetic fields, an invisible and complex force, can be studied here. The collision's chaos has likely twisted and amplified the galaxy's magnetosphere into a turbulent snarl. By mapping the polarized radio light from this invisible web, we can learn how magnetic fields behave when stirred by galactic-sized forces, how they accelerate particles to near light speed, and how they help or hinder the birth of new stars. Every strange phenomenon we have explored, from the ultraluminous X-ray sources to the low metallicity gas, is a data point in this grand experiment. The galaxy pushes our theories to their breaking point, asking questions we are only beginning to formulate. In a lab, you control the conditions to test an idea. In the cosmos, the universe runs the experiments, and we must be clever enough to recognize the setup. The Cartwheel is a once-in-a-lifetime setup, a controlled environment of unimaginable violence, giving us a front-row seat to the physics that shape the universe, written in fire on a canvas 500,000 light-years wide. Its brilliant ring is a clock, and every blue giant is a ticking second hand. The Cartwheel Galaxy, for all its breathtaking scale and symmetry, is not a permanent fixture of the cosmos. It is a temporary masterpiece, a fleeting bloom of stellar fire in a billion-year-long drama of attraction, collision, and slow decay. We are witnessing a single, spectacular scene in a play that has no final curtain, only endless acts of transformation. This ephemeral nature is not a flaw, it is the fundamental truth of a dynamic universe. Nothing out there is static or eternal in its present form. Spiral arms wind up and unravel, elliptical galaxies form from violent mergers, and even the serene islands of stars we see are slowly orbiting toward future encounters that will rewrite their shapes entirely. The Cartwheel's perfect bullseye is a phase, perhaps lasting only a few 100 million of its many billions of years of existence. Soon, in cosmic terms, its fuel will be spent. Its blue giants will fade, and its sharp ring will blur into a more common, amorphous shape. Its beauty is inseparable from its transience. This makes our chance to see it right now, in this precise moment of its life, profoundly precious. It is a coincidence of cosmic timing that feels almost miraculous. That our brief window of consciousness as a curious species overlaps with this brief window of celestial spectacle 500 million light-years away. It invites a deeper reflection. All the grandeur we map in the heavens, the pillars of creation, the swirling nebulae, the majestic spirals, they are all snapshots. They are not monuments but moments. The universe is a river, not a sculpture garden, and we are granted a glimpse of its flow. The Cartwheel teaches us that to understand the cosmos is to embrace impermanence. The violence that creates such beauty is the same force that guarantees its eventual passing, making every clear image, every decoded signal, a priceless fragment of a story that is always being written and erased. Our search for understanding, then, becomes an act of grateful witness, a way of honoring the fleeting splendor of a universe that is forever becoming something new. From the perfect ring born of a direct hit to the missing quasar in its quiet heart, our journey through 50 strange phenomena has taken us across a galaxy sculpted by pure violence. We have witnessed stellar tsunamis, hunted for ghostly dark matter halos, and watched as the wreckage itself gives birth to potential new galaxies. We have seen how a single, piercing collision rewrote the rules of an entire galactic system, leaving behind a landscape of ultraluminous X-ray beacons, chemical anomalies, and magnetic mayhem. This is not merely a beautiful accident. The Cartwheel Galaxy is a cosmic Rosetta Stone. Its clear, perfect form deciphers the chaotic language of galactic collisions, translating the faint whispers from the early universe into a vivid narrative we can understand. It is a natural laboratory where the most extreme physics plays out on a canvas 500,000 light-years wide, testing our theories of star formation, black hole feeding, and the very nature of the invisible dark matter that binds the cosmos. So the next time you look up at a dark, clear sky, remember the cartwheel. Remember that our universe is not a static museum, but a dynamic, evolving arena of breathtaking violence and creativity. Which of its 50 mysteries captivated you the most? Was it the fleeing intruder galaxy, the potential tidal dwarfs, or the profound silence where a monster should roar? Let us know in the comments below and subscribe to keep exploring the deepest wonders hidden